Earth, our beautiful blue marble, our precious home floating in the vast darkness of space, might not actually be the best place in the universe for life to flourish. Tonight we're exploring one of the most profound discoveries in modern astronomy. Scientists have found planets that could be more habitable than Earth itself. Not just potentially habitable, but actually better suited for life than our own world. It's a revelation that challenges everything we thought we knew about what makes a planet perfect for supporting complex ecosystems and thriving biospheres. If you find comfort in these gentle explorations of science, I'd be grateful if you'd consider subscribing and liking this video. The visuals are here for you, but feel free to close your eyes, breathe deep, and let your imagination drift through the galaxy as we discover these remarkable worlds. Also, I'd love to know where you're listening from tonight. Comment your time and location below. Let's begin this cosmic journey together. For centuries, astronomers have searched the night sky for worlds like our own. We've looked for Earth-sized planets orbiting sun-like stars at just the right distance where liquid water could exist on their surfaces. This zone, often called the Goldilocks zone, has been our guiding principle in the hunt for habitable worlds. Not too hot, not too cold, but just right for life as we know it. But here's where the story takes a fascinating turn. What if our entire approach has been too narrow? What if we've been so focused on finding mirror images of Earth that we've overlooked planets that could actually be superior homes for life? Dr. Dirk Schulze-Makuch, an astrobiologist at Washington State University, puts it perfectly when he says we might be overlooking planets that are even more well-suited for life than our own world. This isn't just speculation, it's based on rigorous scientific analysis of the thousands of exoplanets we've discovered beyond our solar system. Think about it for a moment. Earth has experienced mass extinctions, ice ages, asteroid impacts, and countless other catastrophes that have threatened or eliminated entire species. Our planet's habitability has fluctuated dramatically over billions of years. What if there are worlds out there that offer more stable, more nurturing environments for life to develop and thrive? Scientists have now developed a new habitability index that goes far beyond the simple Goldilocks zone concept. This sophisticated framework considers factors like atmospheric composition, stellar radiation levels, geological activity, and orbital dynamics. When they applied this new methodology to thousands of known exoplanets, something remarkable emerged. Some of these distant worlds actually scored higher on the habitability scale than Earth itself. Our planet received a habitability rating of 0.829 on this new index. But there are exoplanets out there with ratings of 0.836 and higher. That might seem like a small difference, but in the precise world of planetary science, these decimal points represent significant improvements in the conditions necessary for life to flourish. Let me paint you a picture of what a superhabitable planet might look like. Imagine a world slightly larger than Earth, perhaps 10% bigger in radius. This extra size would provide more surface area for diverse ecosystems to develop. The increased mass would generate stronger gravity, helping the planet hold onto its atmosphere for billions of years longer than Earth can manage. Picture this world orbiting not a star like our Sun, but an orange dwarf star. These K-type stars are smaller and cooler than our Sun, but they live much longer. While our Sun will burn out in about 10 billion years, Orange dwarfs can shine steadily for 18 to 34 billion years. That's nearly 4 times longer, providing vastly more time for life to evolve, adapt, and reach levels of complexity we can barely imagine. These orange dwarf stars emit just the right amount of ultraviolet radiation, enough to drive beneficial biological processes, but not so much that life needs the protection of a thick ozone layer. The reduced UV output means less radiation damage to DNA, potentially allowing for more stable genetic evolution over geological timescales. Now imagine this superhabitable world with a surface temperature just 5 degrees Celsius warmer than Earth's average. This seemingly modest increase would create a more humid, tropical environment across much of the planet. Higher humidity levels could support more lush vegetation and more productive ecosystems. The additional warmth would prevent the formation of large ice caps at the poles, maximizing the amount of habitable land area available for life to colonize. The atmosphere of such a world might contain 25% oxygen instead of Earth's 21%. This higher oxygen concentration would supercharge biological processes. Plants would photosynthesize more efficiently. Animals would have more energy available for complex behaviors and rapid evolution. The entire biosphere would be more vibrant and productive than anything we see on Earth today. But perhaps most intriguingly, this superhabitable world would have a longer geological history than Earth. Being older means more time for plate tectonics to create diverse landscapes, for evolution to generate incredible biodiversity, and for complex ecosystems to stabilize and mature. While Earth is roughly 4.5 billion years old, some of these superhabitable candidates could be 6, 7, or even 8 billion years old. Think about what life on Earth accomplished in just 4.5 billion years. From simple single-celled organisms to the incredible complexity of modern ecosystems, from the first photosynthetic bacteria to human civilization. Now imagine what might be possible with billions of additional years of uninterrupted evolution on a world with superior environmental conditions. These aren't just theoretical possibilities. We've already identified specific worlds that match these criteria. Take Kepler 442b, located about 1,200 light-years away from Earth. This super-Earth orbits within the habitable zone of an orange dwarf star, receiving just the right amount of stellar energy to maintain liquid water on its surface. With a habitability rating of 0.836, it actually scores higher than Earth on our new assessment scale. Then there's the recently discovered GJ251c, a super-Earth just 20 light-years from our solar system. This world has almost 4 times the mass of Earth and appears to have a rocky composition similar to our own planet. But its location in the habitable zone of a red dwarf star could provide the stable, long-lasting conditions necessary for life to evolve far beyond anything we've seen on Earth. Perhaps most exciting is Gliese 12b, an Earth-like world just 40 light-years away. This planet is slightly smaller than Earth, but receives the perfect amount of energy from its host star to maintain surface temperatures around 42 degrees Celsius. If it has retained an atmosphere, this world could be a tropical paradise with conditions ideal for abundant life. The TRAPPIST-1 system presents us with an entire family of potentially superhabitable worlds. 7 Earth-sized planets orbit this small red dwarf star, and up to 4 of them might exist in the habitable zone. TRAPPIST. 1e stands out as particularly promising, receiving about 60% of the stellar energy that Earth gets from the Sun. This reduced energy input could create more stable climate conditions without the extreme weather patterns that have caused mass extinctions on our own planet. But what makes these discoveries truly revolutionary is how they're changing our entire approach to the search for life in the universe. For decades, we've operated under the assumption that Earth represents the gold standard for habitability. We've looked for planets that are as Earth-like as possible, thinking that familiar conditions would give us the best chance of finding life. Now we're realizing that this Earth-centric bias might have been holding us back. By focusing so intensely on finding exact copies of our own world, we may have been overlooking planets that could support life forms more diverse, more abundant, and more resilient than anything that has ever existed on Earth. Consider the implications. If superhabitable planets are relatively common in our galaxy, then the universe might be far more alive than we ever dared to imagine. These worlds could be teeming with ecosystems that make Earth's rainforests look sparse by comparison. They could be home to evolutionary processes that have been running for billions of years longer than anything on our planet. The search for these superhabitable worlds is being revolutionized by new technologies and observational techniques. NASA's James Webb Space Telescope can analyze the atmospheres of distant exoplanets, looking for chemical signatures that might indicate not just the presence of life, but thriving, abundant life. The Transiting Exoplanet Survey satellite continues to discover new candidate worlds at an unprecedented rate. Ground-based observatories equipped with advanced spectrographs can detect the gravitational wobbles that planets induce in their host stars, allowing us to measure planetary masses with incredible precision. When combined with size measurements from transit observations, we can determine which worlds have the rocky composition necessary to support surface life. But perhaps most remarkably, we're beginning to detect atmospheric compositions that could indicate superhabitable conditions, planets with higher oxygen concentrations, increased water vapor content, and atmospheric chemistries that suggest robust biological activity. These aren't just potentially habitable worlds. They're worlds where life might be thriving in ways that surpass anything in Earth's history. The closest of these superhabitable candidates is Proxima Centauri b, just over 4 light-years away. This Earth-mass world orbits in the habitable zone of the nearest star to our Sun. It receives about 65% of the energy that Earth gets, which could create more stable climate conditions. Depending on its atmospheric evolution, Proxima b could have vast oceans and an oxygen-rich atmosphere supporting ecosystems more diverse than anything on Earth. Scientists are already planning missions to study these worlds in detail. Future space telescopes will be able to analyze their atmospheric compositions, search for biosignatures, and even potentially detect surface features that might indicate the presence of life. Within the next decade, we might know definitively whether some of these superhabitable planets are indeed more hospitable to life than our own world. The implications extend far beyond astronomy and astrobiology. If we confirm that superhabitable planets exist and are relatively common, it would represent one of the most significant discoveries in human history. It would tell us that the universe is not only alive, but that it's far more alive than we ever imagined. These worlds challenge our assumptions about what makes a planet perfect for life. They suggest that the conditions we consider normal and optimal on Earth might actually be somewhat limited compared to what's possible elsewhere in the galaxy. Earth might be a good planet for life, but not necessarily the best planet for life. As we continue our exploration of these remarkable worlds, we'll discover how scientists are identifying the specific characteristics that make a planet superhabitable, how we're detecting and studying these distant worlds with unprecedented precision, and what the existence of superhabitable planets might mean for the future of life in the universe. The detection of these superhabitable worlds represents a fundamental shift in how we understand planetary formation and stellar evolution. You see, when astronomers first began discovering exoplanets in the 1990s, they found mostly what we call hot Jupiters, massive gas giants orbiting impossibly close to their host stars. These worlds taught us that planetary systems could be radically different from our own solar system, but they seemed utterly hostile to life as we know it. As our detection methods improved, we began finding smaller, rockier planets in the habitable zones of their stars. Each discovery brought excitement, but also a nagging question that kept astronomers awake at night. Were we simply finding more versions of Earth, or was there something fundamentally different about how life could emerge and thrive on other worlds? The answer came from an unexpected direction. Instead of just cataloguing planets that resembled Earth, scientists began asking a more profound question. What if Earth itself isn't the pinnacle of habitability? What if the conditions that gave rise to life on our planet represent just one possible pathway among many, and not necessarily the best one? This revolutionary thinking led researchers to examine the characteristics that truly matter for supporting complex, long-lasting biospheres. They looked beyond the simple presence of liquid water and began considering factors like atmospheric stability, stellar longevity, geological activity, and orbital dynamics. What emerged was a picture of planetary habitability far more nuanced and exciting than anyone had previously imagined. Consider the role of planetary mass in creating superhabitable conditions. Earth's mass generates enough gravity to hold onto our atmosphere, but just barely. Over geological time, we're slowly losing our atmospheric envelope to space. A planet with 10 to 50% more mass than Earth would have stronger gravitational binding, allowing it to retain its atmosphere for much longer periods. This extended atmospheric stability could support life for billions of additional years beyond Earth's projected habitability timeline. The increased mass also drives more vigorous geological activity through enhanced radioactive decay in the planet's interior. This sustained geological engine powers plate tectonics for extended periods, recycling nutrients through the biosphere and maintaining the chemical cycles that life depends upon. On Earth, our plate tectonics may shut down in 1 billion years as our planet's interior cools. Superhabitable worlds could maintain active geology for 10 times longer. But perhaps most fascinating is how stellar properties influence planetary habitability. Our Sun is what astronomers classify as a G-type yellow dwarf star. It served us well, providing stable energy output for billions of years. But G-type stars have some significant limitations when it comes to supporting life over cosmic timescales. The Sun's energy output increases steadily over time due to changes in its core composition. In about 1 billion years, it will be 10% brighter than today, enough to trigger a runaway greenhouse effect that will boil away Earth's oceans. Eventually, our Sun will expand into a red giant, rendering the entire inner solar system uninhabitable. The total window for complex life around a star like our Sun spans perhaps 8 to 10 billion years. Now contrast this with K-type orange dwarf stars, which make up about 12% of all stars in our galaxy. These stellar engines burn their nuclear fuel more slowly and efficiently than our Sun. They maintain stable energy output for 20 to 40 billion years, providing nearly 4 times longer for life to evolve and develop complexity. The extended stellar lifetimes mean that superhabitable planets orbiting these stars could host continuous biological evolution for periods that dwarf Earth's entire history. The radiation environment around orange dwarfs also proves more favorable for life. These stars emit less harmful ultraviolet radiation than our Sun, reducing the risk of genetic damage to surface-dwelling organisms. At the same time, they produce enough UV to drive important atmospheric chemistry and biological processes. It's a perfect balance that could allow life to thrive on planetary surfaces without requiring the complex ozone layer that protects Earth's biosphere. The habitable zones around orange dwarfs are also more stable than around Sun-like stars. As these long-lived stars age, their energy output changes very gradually, keeping planets in the habitable zone for extended periods. Earth will eventually migrate out of our Sun's habitable zone as solar brightness increases. But superhabitable planets around orange dwarfs could remain in the sweet spot for tens of billions of years. Recent atmospheric modeling reveals another crucial advantage of superhabitable worlds. Computer simulations suggest these planets could maintain higher humidity levels and more extensive cloud cover than Earth. This enhanced atmospheric moisture content would create more stable global climate patterns, reducing the risk of the extreme climate swings that have triggered mass extinctions throughout Earth's history. Higher humidity also supports more productive ecosystems. Think about the difference between Earth's tropical rainforests and its desert regions. The rainforests teem with biodiversity precisely because of their warm, humid conditions. A superhabitable planet with globally elevated humidity could support rainforest-like productivity across much larger areas of its surface. The atmospheric composition of superhabitable worlds opens even more intriguing possibilities. While Earth's atmosphere contains 21% oxygen, some models suggest that 25% oxygen could be optimal for supporting complex life. This higher oxygen concentration would increase the efficiency of cellular respiration in animals and boost the productivity of photosynthetic plants. Higher oxygen levels would also support larger, more active organisms. During Earth's Carboniferous period, when atmospheric oxygen reached 23%, we saw giant insects and other creatures that couldn't survive in today's lower oxygen environment. A superhabitable world with sustained high oxygen levels could support even more impressive megafauna throughout its evolutionary history. The carbon dioxide levels on superhabitable planets also play a crucial role. Moderate CO2 concentrations help maintain warm global temperatures through the greenhouse effect, while also providing the raw material for photosynthesis. The ideal superhabitable world might maintain CO2 levels that optimize both temperature regulation and biological productivity, but atmospheric composition is just one piece of the superhabitable puzzle. The orbital characteristics of these worlds could provide additional advantages over Earth's somewhat chaotic orbital situation. Our planet's orbit is nearly circular, which provides stable seasons and climate patterns. However, some research suggests that moderate orbital eccentricity could actually enhance habitability by creating more diverse climate zones and driving atmospheric circulation patterns that distribute heat and moisture more effectively. Similarly, planets with higher obliquity, meaning their rotational axes are tilted more than Earth's 23.5 degrees, could experience more dramatic seasonal variations. While this might sound less hospitable, it could actually promote greater biodiversity by creating more ecological niches and driving evolutionary adaptation. The age factor in superhabitable planets deserves special attention. Earth formed about 4.5 billion years ago, and life appeared relatively quickly in geological terms. But complex multicellular life didn't emerge until about 600 million years ago, and human-level intelligence only within the last few million years. This timeline suggests that biological complexity increases with planetary age, given stable environmental conditions. Superhabitable planets that are 6, 7, or 8 billion years old would have had additional billions of years for evolution to operate. The level of biological complexity and diversity on such ancient worlds could be staggering. We might find ecosystems with intricate relationships between thousands of species, evolutionary adaptations that seem almost magical, and perhaps even forms of intelligence that dwarf our own cognitive abilities. The geological evolution of superhabitable planets also offers advantages over Earth's development. Our planet's continents and ocean basins have been shaped by the random impacts of asteroids, volcanic activity, and the gradual cooling of our interior. Older planets would have had more time for these processes to create optimal configurations of land and water that maximize habitability. Imagine continents arranged in patterns that optimize global climate regulation, with inland seas and mountain ranges positioned to create the most favorable conditions for life. Picture ocean basins with the perfect depth and circulation patterns to maintain stable temperatures and distribute nutrients efficiently throughout marine ecosystems. Given billions of additional years, geological processes could sculpt planetary surfaces into configurations far more hospitable than Earth's somewhat random arrangement. The magnetic field strength of superhabitable planets could also surpass Earth's protective capabilities. Our magnetic field, generated by the motion of liquid iron in our planet's core, shields us from harmful solar radiation and cosmic rays. Larger planets with more massive cores could generate stronger, more stable magnetic fields that provide superior protection for surface life. These enhanced magnetic fields would be particularly important for planets orbiting red dwarf stars, which can produce intense stellar flares that would otherwise strip away planetary atmospheres. A superhabitable world with a robust magnetic field could maintain its atmospheric envelope even when subjected to the occasional stellar tantrums that characterize smaller stars. The discovery methods for identifying superhabitable planets continue to evolve at a remarkable pace. The transit photometry technique, which detects the slight dimming of starlight as planets pass in front of their host stars, has already revealed thousands of exoplanets. But newer approaches are pushing the boundaries of what we can learn about distant worlds. Radial velocity measurements can now detect the gravitational wobbles induced by planets with incredible precision. The espresso spectrograph can measure stellar motion changes as small as 10 centimeters per second, allowing astronomers to identify Earth-mass planets around nearby stars. When combined with transit observations, these measurements reveal planetary densities that tell us whether we're looking at rocky worlds capable of supporting surface life. Direct imaging of exoplanets represents the holy grail of planet detection. While incredibly challenging due to the overwhelming brightness of host stars, new techniques using coronagraphs and adaptive optics are beginning to capture actual photographs of giant planets orbiting distant stars. Future space telescopes will extend this capability to smaller, potentially habitable worlds. Atmospheric spectroscopy through transit observations offers perhaps the most exciting avenue for studying superhabitable planets. When a planet passes in front of its star, some starlight filters through the planetary atmosphere, carrying chemical fingerprints that reveal atmospheric composition. The James Webb Space Telescope has already begun detecting water vapor, carbon dioxide, and other molecules in exoplanet atmospheres. For superhabitable worlds, atmospheric spectroscopy could reveal the enhanced oxygen levels, optimal humidity, and complex chemistry that characterize truly superior biospheres. We might even detect industrial pollutants or other technosignatures that would indicate the presence of advanced civilizations that have had billions of additional years to develop beyond our current technological level. The statistical analysis of exoplanet populations is revealing that superhabitable worlds might be surprisingly common in our galaxy. Early estimates suggest that 20 to 30% of stars host planets in their habitable zones. If even a fraction of these worlds qualify as superhabitable, the Milky Way could contain billions of planets where life thrives under conditions superior to those on Earth. This abundance of potentially superior worlds raises profound questions about our place in the cosmic order. If Earth represents merely an adequate habitat for life rather than an optimal one, what does this tell us about the prevalence of biological complexity throughout the universe? The answer might be more remarkable than we ever dared to hope. The implications stretch far beyond simple planetary statistics. If superhabitable worlds are indeed common, we may need to completely reimagine our understanding of how life develops across cosmic time. Consider this sobering possibility. While we've spent centuries assuming Earth represents the pinnacle of biological potential, we might actually be living on what amounts to a marginally habitable world compared to the cosmic standard. This revelation carries both humbling and inspiring dimensions. On one hand, it suggests that life throughout the galaxy could be far more abundant, diverse, and sophisticated than our Earth-based experience has led us to believe. On the other hand, it opens extraordinary possibilities for understanding what life might achieve given truly optimal conditions. Let's explore what this means for our search strategies. Traditional approaches to finding extraterrestrial life have focused on detecting Earth-like biosignatures, oxygen paired with water vapor, seasonal variations in atmospheric chemistry, or the infrared signatures of chlorophyll-based photosynthesis. But if superhabitable planets support more vigorous biospheres, their biosignatures might be dramatically more obvious than anything we'd expect from Earth analog worlds. Picture a planet where enhanced oxygen levels and optimal humidity create forest ecosystems so productive they cover 90% of the landmass. The atmospheric signatures from such a world would practically scream biological activity across interstellar distances. Seasonal variations in atmospheric composition would be more pronounced as vast continental forests synchronize their growth and dormancy cycles. The infrared glow from dense vegetation would be detectable even with current telescope technology. But the biosignatures from superhabitable worlds might extend beyond anything we recognize from Earth's biosphere. Higher atmospheric oxygen could support chemistries unknown in our experience. The enhanced geological activity on these worlds might drive nutrient cycles that create entirely novel forms of biological organization. We might discover atmospheric compounds that have no terrestrial equivalent, but represent the waste products of alien metabolisms operating under superior environmental conditions. The temporal aspect of superhabitable planets introduces another layer of complexity to our search efforts. While Earth's biosphere has existed for roughly 3.5 billion years, these ancient worlds could host biological systems that have been evolving for 6, 7, or 8 billion years. The sheer duration of uninterrupted biological evolution could produce ecosystems of staggering sophistication. Think about how much Earth's biosphere has changed in just the last 500 million years since the Cambrian explosion. We've seen the rise of complex multicellular organisms, the colonization of land by plants and animals, the evolution of flight, the development of social behaviors, and ultimately the emergence of technology using intelligence. Now imagine what might be possible with an additional 4 billion years of continuous evolution under superior environmental conditions. The civilizations that might arise on superhabitable worlds could possess technological capabilities that dwarf our current achievements. While human civilization has existed for mere thousands of years, intelligent species on these ancient worlds might have had millions or even billions of years to develop science, technology, and perhaps forms of organization we cannot yet conceive. This possibility introduces fascinating considerations for our search for extraterrestrial intelligence. Rather than looking for radio signals or other signatures of early technological development, we might need to search for evidence of mature civilizations that have had geological ages to perfect their relationship with their planetary environment. Such advanced societies might have learned to manage their atmospheric composition with precision, creating artificial biosignatures that optimize planetary conditions for continued biological flourishing. They might have developed energy systems so efficient and clean that they leave no detectable waste heat or electromagnetic signatures. Their presence might be marked not by industrial pollution or radio broadcasts, but by the subtle perfection of planetary-scale ecological engineering. The search for these mature technological signatures requires entirely new approaches to astronomical observation. We're learning to look for patterns in planetary atmospheric composition that might indicate deliberate management rather than natural processes. We're developing techniques to detect the infrared signatures of advanced materials that don't occur naturally. We're even considering whether certain orbital configurations of multiple planets might represent evidence of large-scale engineering projects. But perhaps most intriguingly, we're beginning to understand that superhabitable planets might support forms of intelligence that operate on completely different principles than human cognition. Earth's evolutionary history has been shaped by periodic mass extinctions, resource limitations, and environmental instability. These pressures have favored intelligence that excels at rapid adaptation, tool use, and environmental manipulation. Superhabitable worlds with their stable, nurturing environments might have fostered the evolution of intelligence optimized for different purposes. Perhaps forms of consciousness that excel at long-term thinking, operating on timescales of thousands or millions of years. Maybe cognitive architectures that prioritize cooperation and ecological integration over competition and environmental domination. The possibility that intelligence might evolve differently under superhabitable conditions challenges our assumptions about what to look for when searching for signs of extraterrestrial civilization. We've been scanning the skies for signals similar to our own radio and television broadcasts, assuming that technological development follows a universal pattern. But civilizations that emerged on superhabitable worlds might have developed along entirely different trajectories. Consider how different human history might have been if Earth had never experienced mass extinctions, ice ages, or resource scarcity. Would we have developed the same drive to explore, to innovate, to push beyond planetary boundaries? Or might we have evolved into something more contemplative, more integrated with our biosphere, perhaps less recognizable as intelligence from our current perspective? These questions become more than philosophical speculation when we consider the practical implications for interstellar communication. If superhabitable worlds have indeed produced forms of intelligence vastly different from our own, establishing meaningful contact might require entirely new approaches to cross-species communication. We might need to develop methods for recognizing and interpreting forms of intelligence that operate on different timescales, with different priorities, and through different sensory modalities than our own. The atmospheric analysis techniques we're developing to study superhabitable planets are revealing unprecedented details about distant world compositions. Spectroscopic observations can now detect trace gases present at concentrations of just a few parts per million in exoplanet atmospheres. This sensitivity opens the possibility of identifying not just major atmospheric components like oxygen and water vapor, but also the subtle chemical signatures that might indicate biological or even technological activity. For instance, the simultaneous presence of oxygen and methane in a planetary atmosphere represents a powerful biosignature, since these gases react with each other and disappear unless continuously replenished by biological processes. On superhabitable worlds with enhanced biological productivity, we might detect these biosignature pairs at much higher concentrations than would be possible on Earth-like planets. Similarly, certain industrial compounds like nitrogen oxides or fluorinated gases would represent unambiguous technosignatures if detected in exoplanet atmospheres. Advanced civilizations on superhabitable worlds might use such compounds in ways we haven't yet imagined, creating atmospheric signatures that would immediately indicate the presence of intelligence capable of large-scale chemical engineering. The gravitational microlensing technique offers another powerful tool for discovering superhabitable planets around distant stars. When a foreground star passes almost directly between Earth and a background star, the gravitational field of the foreground star acts like a lens, magnifying the light from the background star. If the foreground star hosts planets, they create additional brightening events that reveal their presence and characteristics. Microlensing surveys can detect planets at much greater distances than other techniques, potentially revealing superhabitable worlds throughout the galactic disk. Unlike transit observations, which require planets to orbit edge-on from our perspective, microlensing can detect planets regardless of their orbital orientation. This technique might reveal populations of superhabitable worlds that remain invisible to other detection methods. The upcoming Nancy Grace Roman Space Telescope will conduct the most comprehensive microlensing survey ever attempted, potentially discovering thousands of new exoplanets including many in the superhabitable category. Combined with atmospheric characterization from the James Webb Space Telescope and future observatories, we're entering an era where we can not only find these superior worlds, but also study their conditions in unprecedented detail. Ground-based telescopes are also contributing crucial observations to our understanding of superhabitable planets. The extremely large telescopes currently under construction will have mirrors 30 to 40 meters in diameter, providing unprecedented resolution and light-gathering power. These instruments will be capable of directly imaging potentially habitable exoplanets around nearby stars and analyzing their atmospheric spectra with extraordinary precision. The combination of space-based and ground-based observations is creating a comprehensive picture of planetary diversity that extends far beyond our solar system experience. We're discovering that planets can maintain stable atmospheres under a much wider range of conditions than previously thought. We're learning that biological activity can thrive in environments that would be considered extreme by Earth standards. And we're realizing that the universe might be far more hospitable to life than our Earth-centric perspective has suggested. The theoretical models that predict superhabitable conditions are becoming increasingly sophisticated as our computational capabilities advance. Climate modeling software can now simulate the atmospheric dynamics of exoplanets with remarkable accuracy, taking into account factors like stellar radiation, planetary rotation, atmospheric composition, and surface geography. These models reveal the complex interplay of factors that determine whether a planet can maintain conditions suitable for advanced life. Perhaps most remarkably, some of these climate models suggest that superhabitable planets might be able to maintain stable, life-friendly conditions, even when subjected to environmental perturbations that would devastate Earth's biosphere. The enhanced atmospheric mass and improved heat distribution on these worlds could provide resilience against asteroid impacts, volcanic eruptions, or stellar variability that would trigger mass extinctions on less robust planets. This environmental stability has profound implications for the development of complexity on superhabitable worlds. While Earth's history has been punctuated by catastrophic events that reset evolutionary progress, these superior planets might support uninterrupted biological development for billions of years. The cumulative effect of such extended, stable evolution could produce levels of biological sophistication that we can barely imagine. As we continue our exploration of these remarkable worlds, we're beginning to understand that the universe might be not just alive, but vibrantly, abundantly alive in ways that exceed our wildest scientific dreams. The superhabitable planets scattered throughout our galaxy represent possibilities for life that transcend everything we thought we knew about biological potential. They offer glimpses of what might be possible when evolution operates under truly optimal conditions, free from the constraints and catastrophes that have limited life's development on our own world. The search for biosignatures on these superhabitable worlds is revealing patterns that challenge our fundamental assumptions about how life announces its presence across interstellar distances. Traditional biosignature detection has focused on finding combinations of gases that shouldn't coexist in a sterile atmosphere, like oxygen and methane existing simultaneously. But the enhanced biological productivity possible on superhabitable planets could create atmospheric signatures so robust they're detectable with instruments we're building today. Picture atmospheric oxygen concentrations reaching 25 or even 30%. levels that would create infrared absorption features visible across dozens of light years. Imagine water vapor signatures so strong they indicate not just the presence of liquid water, but vast ocean systems with active hydrological cycles that dwarf anything on Earth. These aren't subtle hints of biological activity. They're atmospheric compositions that practically announce the presence of thriving biospheres to anyone with a telescope powerful enough to detect them. But perhaps most intriguingly, we're beginning to understand that life on superhabitable worlds might produce entirely novel atmospheric chemistries. The combination of higher oxygen levels, enhanced geological activity, and billions of additional years of biological evolution could give rise to metabolisms that create atmospheric byproducts unknown on Earth. We might discover trace gases that represent the waste products of alien biochemistries operating under superior environmental conditions. The dimethyl sulfide signatures we're learning to detect offer a perfect example of how biological activity can leave unmistakable atmospheric fingerprints. On Earth, this compound is produced primarily by marine organisms and represents one of the most promising biosignatures for remote detection. But on superhabitable worlds with more extensive ocean systems and higher biological productivity, dimethyl sulfide concentrations could be orders of magnitude higher than anything we see in Earth's atmosphere. Recent studies suggest that just a few percent surface coverage of biological activity on nearby exoplanets might be sufficient for detection with next-generation telescopes. If superhabitable worlds truly support more abundant and diverse life than Earth, their biosignatures should be correspondingly more obvious. We might be on the verge of discovering not just that life exists elsewhere, but that it exists in forms more vibrant and productive than anything in our terrestrial experience. The atmospheric modeling for these worlds reveals another fascinating possibility. The enhanced humidity and temperature stability predicted for superhabitable planets could support global cloud formations that create unique spectroscopic signatures. These aren't just weather patterns, but atmospheric dynamics that could indicate the presence of planet-wide biological cycles operating on scales impossible under Earth's more limited conditions. Consider how seasonal variations in atmospheric composition might appear on a superhabitable world, where 90% of the land surface supports dense vegetation. The synchronized growth and dormancy cycles of such extensive forest ecosystems would create atmospheric oscillations detectable across interstellar distances. We might observe carbon dioxide concentrations fluctuating with seasonal rhythms, but with amplitudes that dwarf anything seen in Earth's atmosphere. The search for technosignatures on superhabitable worlds opens even more extraordinary possibilities. While human civilization has existed for mere thousands of years, intelligent species on these ancient planets might have had millions or billions of years to develop technologies we can't yet imagine. Their atmospheric signatures might reflect not industrial pollution, but sophisticated environmental engineering designed to optimize planetary conditions for continued biological flourishing. Advanced civilizations on superhabitable worlds might have learned to manage their atmospheric composition with precision that appears almost magical from our current technological perspective. They could maintain perfect ratios of greenhouse gases to regulate global temperatures, engineer atmospheric chemistry to maximize biological productivity, or even create artificial atmospheric layers that protect surface life from cosmic radiation. These possibilities require us to expand our definition of what constitutes evidence for extraterrestrial intelligence. Rather than searching for radio signals or industrial pollutants, we might need to look for atmospheric compositions that are too perfect, too finely tuned to have arisen through natural processes alone. The signature of advanced intelligence might be not the presence of technology, but the subtle perfection of planetary-scale ecological management. The orbital dynamics of superhabitable worlds also contribute to their superior conditions in ways we're only beginning to understand. While Earth's nearly circular orbit provides relatively stable seasonal patterns, some research suggests that moderate orbital eccentricity could actually enhance habitability by creating more diverse climate zones and driving atmospheric circulation patterns that distribute heat and moisture more effectively across planetary surfaces. Similarly, planets with higher axial tilts than Earth's 23.5 degrees could experience more dramatic seasonal variations that promote greater biodiversity by creating additional ecological niches. The enhanced seasonal contrasts might drive evolutionary adaptations that produce more resilient and diverse biological communities than Earth's relatively stable seasonal patterns have fostered. The magnetic field configurations of superhabitable worlds represent another crucial advantage over Earth's protective capabilities. Larger planets with more massive metallic cores could generate magnetic fields significantly stronger than Earth's magnetosphere. These enhanced magnetic shields would provide superior protection against cosmic radiation and stellar particle bombardment, allowing surface life to thrive even around more active stars. The implications become particularly important for planets orbiting red dwarf stars, which comprise roughly 75% of all stars in our galaxy. Red dwarfs are known for producing intense stellar flares that could strip away planetary atmospheres over geological time. But superhabitable worlds with robust magnetic fields could maintain their atmospheric envelopes, even when subjected to these occasional stellar outbursts. The geological evolution of superhabitable planets offers advantages that extend far beyond simple planetary age. The enhanced radioactive decay in more massive worlds drives vigorous geological activity for extended periods, recycling nutrients through the biosphere and maintaining the chemical cycles that complex life depends upon. While Earth's plate tectonics may cease in a billion years as our planet's interior cools, superhabitable worlds could maintain active geology for tens of billions of years. This sustained geological activity creates opportunities for biological evolution that simply don't exist on Earth. The continuous recycling of surface materials brings fresh nutrients to biological systems while removing toxic waste products. The ongoing creation of diverse geographical features provides new ecological niches for life to colonize. The stable maintenance of atmospheric composition through geological processes creates environmental conditions that remain optimal for biological activity across cosmic timescales. But perhaps most remarkably, the extended geological activity on superhabitable worlds could produce continental configurations optimized for supporting life. Given billions of additional years, geological processes could arrange continents and ocean basins in patterns that maximize global climate stability, create optimal ocean circulation patterns, and provide the most favorable conditions for biological productivity. Imagine continents positioned to regulate global temperature through optimal albedo patterns, with mountain ranges oriented to create beneficial weather systems, and inland seas located to moderate regional climate extremes. Picture ocean basins with depths and shapes that optimize nutrient circulation and maintain stable marine ecosystems. These aren't random geographical accidents, but the products of extended geological evolution operating under enhanced planetary conditions. The deep time perspective of superhabitable planets forces us to confront possibilities that challenge our understanding of what evolution can accomplish given sufficient time and optimal conditions. Earth's evolutionary history spans roughly 3.5 billion years, during which life has progressed from simple single-celled organisms to the complex biosphere we observe today. But this progression has been repeatedly interrupted by mass extinction events, ice ages, and environmental catastrophes that reset evolutionary progress. Superhabitable worlds with their enhanced environmental stability could support uninterrupted biological evolution for 6, 7, or 8 billion years. The cumulative effect of such extended development under optimal conditions could produce ecosystems of breathtaking sophistication. We might find biological systems with intricate relationships between thousands of species, evolutionary adaptations that seem almost magical by Earth standards, and levels of ecosystem integration that represent the full flowering of biological potential. The nitrogen cycle management on these worlds could achieve efficiencies unknown on Earth. The carbon sequestration systems could maintain atmospheric composition with precision that rivals technological control systems. The biodiversity patterns could create ecosystem resilience that prevents the kind of cascading collapses that characterize Earth's environmental history. But beyond these enhanced biological systems, superhabitable worlds might support the emergence of intelligence forms that operate on fundamentally different principles than human cognition. Earth's evolutionary pressures have favored intelligence that excels at rapid adaptation, tool use, and environmental manipulation. The stable, nurturing conditions on superhabitable worlds might have fostered cognitive architectures optimized for entirely different purposes. Perhaps forms of consciousness that excel at long-term thinking, operating on timescales of millennia rather than decades. Maybe intelligence that prioritizes ecological integration over environmental domination, developing technologies that enhance rather than exploit natural systems. The cognitive diversity possible under superhabitable conditions could produce minds as different from human intelligence as human minds differ from those of other Earth species. The communication systems used by such intelligences might operate through mechanisms we haven't yet conceived. Rather than electromagnetic signals, they might utilize atmospheric chemistry modifications, geological pattern creation, or biological system orchestration to convey information across planetary or even interstellar distances. Their presence might be marked not by radio telescopes and television broadcasts, but by the subtle coordination of planetary-scale biological and geological processes. These possibilities require us to expand our search methodologies beyond the narrow focus on human-like technological signatures. We're developing techniques to recognize patterns in atmospheric composition that might indicate deliberate management rather than natural processes. We're learning to identify infrared signatures that could represent advanced materials or energy systems unknown to our current technology. The statistical modeling of galactic populations suggests that superhabitable worlds might be surprisingly common throughout the Milky Way. Current estimates indicate that 20 to 30% of stars host planets within their habitable zones. If even a fraction of these worlds qualify as superhabitable, Our galaxy could contain billions of planets where life thrives under conditions superior to Earth's environment. This abundance of potentially superior worlds transforms our understanding of life's prevalence throughout the universe. Rather than representing rare oases of biological activity in a largely sterile cosmos, planets might be common venues for biological experimentation on scales that dwarf Earth's achievements. The universe might teem with worlds where life has had billions of additional years to explore evolutionary possibilities we can barely imagine. The technological trajectory analysis for civilizations on superhabitable worlds suggests development patterns that diverge dramatically from human experience. While our species has progressed from stone tools to space technology in just a few thousand years, intelligent species on ancient superhabitable worlds might have had millions of times longer to perfect their relationship with their planetary environment. Such mature technological civilizations might have transcended the resource limitations and environmental conflicts that characterize human development. They could have achieved energy systems so efficient they leave no detectable waste signatures. Material sciences so advanced they can manipulate matter at the atomic level, and ecological integration so complete they enhance rather than degrade their planetary biosphere. The observational strategies for detecting and studying these remarkable worlds are evolving rapidly as our instrumental capabilities advance. The James Webb Space Telescope has already begun revolutionizing atmospheric characterization of exoplanets, detecting water vapor, carbon dioxide, and complex atmospheric dynamics on worlds dozens of light years away. Future space telescopes will extend these capabilities to smaller, more Earth-like worlds around nearby stars. The upcoming extremely large telescopes will provide unprecedented resolution and sensitivity for direct imaging of potentially habitable exoplanets. These ground-based instruments will complement space-based observations by providing detailed spectroscopic analysis of planetary atmospheres and surface compositions. The combination of space and ground-based observations will create comprehensive portraits of superhabitable worlds that reveal their true potential for supporting advanced life. But perhaps most importantly, the discovery of superhabitable planets is transforming our perspective on humanity's place in the cosmic order. If Earth represents merely an adequate habitat for life, rather than an optimal one, what does this tell us about our species' potential for growth and development? The existence of superior worlds suggests possibilities for biological and intellectual advancement that transcend our current limitations. The humbling realization that we might inhabit a marginally habitable world compared to cosmic standards carries profound implications for how we view our planetary stewardship responsibilities. If superhabitable conditions are achievable through natural processes, perhaps human technology could eventually transform Earth into a more optimal environment for supporting diverse, abundant life. The inspirational dimension of superhabitable planet research lies in its revelation that the universe might be far more alive, more vibrant, and more hospitable to intelligence than our earthbound experience has suggested. These worlds represent not just scientific curiosities, but glimpses of what biological evolution can achieve when operating under truly favorable conditions for extended periods of cosmic time. As we continue developing the technologies necessary to study these distant worlds in detail, We stand at the threshold of discoveries that could fundamentally transform human understanding of life's potential throughout the universe. The superhabitable planets scattered across our galaxy might hold the keys to comprehending what consciousness, intelligence, and biological complexity can become when freed from the constraints that have limited their development on our own remarkable but perhaps not optimal world. The gravitational wave signatures from superhabitable worlds could reveal geological processes operating on scales that dwarf anything we observe on Earth. When massive planetary systems undergo tectonic activity, they generate ripples in space-time itself that propagate across the galaxy at light speed. The enhanced geological vigor of these larger, more active worlds might produce gravitational wave patterns detectable by our most sensitive instruments, providing insights into planetary dynamics that remain invisible to traditional astronomical observation. Consider the implications of discovering gravitational waves generated by superhabitable planet formation processes. These signals could reveal how enhanced accretion disks around orange dwarf stars create the optimal conditions for building worlds superior to Earth. The gravitational fingerprints of planetary migration, atmospheric evolution, and even large-scale biological processes might be encoded in the space-time distortions reaching our detectors. The tidal forces operating in superhabitable planetary systems offer another avenue for enhanced habitability that we're only beginning to appreciate. Planets with multiple large moons could experience complex tidal cycles that drive enhanced ocean mixing, bringing nutrients from the deep ocean to surface layers where photosynthetic organisms can access them. These dynamic tidal systems could create marine ecosystems more productive and diverse than anything in Earth's geological record. The enhanced tidal mixing would also help regulate global climate by distributing heat more efficiently throughout planetary ocean systems. Unlike Earth's relatively simple tidal patterns driven by our single large moon, superhabitable worlds could experience intricate tidal rhythms that optimize conditions for marine life while maintaining stable global temperatures across geological timescales. But the story becomes even more fascinating when we consider how these tidal forces might influence atmospheric dynamics on superhabitable worlds. The gravitational interactions between multiple moons and their host planet could drive atmospheric circulation patterns that transport moisture and heat with unprecedented efficiency. These enhanced weather systems might prevent the formation of permanent ice caps while ensuring adequate rainfall reaches all continental regions. The atmospheric pressure profiles of superhabitable planets reveal another dimension of their superiority over Earth-like conditions. Worlds with enhanced atmospheric mass could maintain higher surface pressures that allow liquid water to exist across broader temperature ranges. This expanded liquid water stability zone would permit surface life to thrive in regions that would be frozen wastelands or boiling deserts under Earth's atmospheric conditions. Higher atmospheric pressure also enhances the efficiency of gas exchange processes crucial for advanced life forms. The increased density of atmospheric gases improves respiratory efficiency for complex organisms, while providing more effective protection against harmful cosmic radiation. These dense atmospheres could support larger, more active life forms than Earth's relatively thin atmospheric envelope permits. The chemical weathering processes on superhabitable worlds operate under conditions that could maintain optimal soil chemistry for extended geological periods. The enhanced geological activity continuously exposes fresh rock to weathering processes, releasing essential nutrients into soil systems while preventing the accumulation of toxic compounds that could limit biological productivity. This sustained nutrient cycling creates agricultural conditions that remain fertile across cosmic timescales. The soil development on these worlds benefits from billions of additional years of biological activity, enriching sedimentary layers with organic compounds. The deep, nutrient-rich soils that result from extended biological and geological processes could support plant communities with root systems and nutrient uptake capabilities far exceeding anything in Earth's ecosystems. But perhaps most remarkably, the symbiotic relationships between geological and biological processes on superhabitable worlds might achieve integration levels that transform entire planets into unified living systems. The enhanced chemical communication between organisms, facilitated by optimal atmospheric conditions and soil chemistry, could create planetary-scale coordination of biological activity that optimizes ecosystem function on a global scale. The seasonal patterns on superhabitable worlds with optimal axial tilts could drive biological cycles that enhance rather than stress planetary ecosystems. Unlike Earth's sometimes harsh seasonal transitions that can trigger ecosystem collapses, the moderate seasonal variations on these worlds might create rhythmic patterns that synchronize reproduction, migration, and growth cycles across multiple species simultaneously. These coordinated biological rhythms could produce atmospheric oscillations that help regulate global climate while maximizing the efficiency of nutrient cycling throughout planetary ecosystems. The seasonal release and uptake of atmospheric gases by synchronized biological communities could maintain optimal atmospheric composition without requiring technological intervention. The evolutionary pressures operating on superhabitable worlds differ fundamentally from those that shaped life on Earth. While our planet's history of catastrophic events has favored organisms capable of rapid adaptation and survival under extreme conditions, the stable environments of superhabitable worlds might promote the evolution of species optimized for cooperation, efficiency, and long-term ecological integration. These different evolutionary pressures could produce biological communities with unprecedented levels of interspecies cooperation and resource sharing. Rather than the competitive dynamics that characterize many Earth ecosystems, superhabitable worlds might support collaborative biological networks that maximize ecosystem productivity while minimizing waste and conflict. The energy efficiency achievements possible under superhabitable conditions could create biological systems that approach theoretical limits of thermodynamic optimization. The combination of enhanced atmospheric conditions, optimal stellar radiation, and superior nutrient cycling could support photosynthetic processes with efficiency levels that dwarf anything observed in Earth's plant communities. These highly efficient biological energy systems could support ecosystem complexity that transcends our current understanding of what's possible through natural processes. The enhanced energy availability might permit the evolution of biological structures and behaviors that seem almost technological in their sophistication and coordination. The information processing capabilities that might emerge from such optimized biological systems challenge our assumptions about the boundaries between biological and technological intelligence. Neural networks that develop under superhabitable conditions, with access to superior nutrition and protection from environmental stressors could achieve computational capabilities that rival or exceed artificial intelligence systems developed through technological means. The collective intelligence possible when billions of highly optimized organisms coordinate their activities across planetary scales might represent forms of consciousness that operate according to principles we haven't yet discovered. These planetary scale minds might process information and make decisions using biological architectures that integrate seamlessly with their planetary environment. The temporal perspectives of such intelligences could encompass timescales that dwarf human historical experience. Consciousness that emerges from biological systems with lifespans measured in millennia rather than decades might develop philosophical and scientific understanding that transcends our current intellectual frameworks. The scientific methodologies employed by civilizations with access to billions of years of continuous observation and experimentation could produce knowledge systems of staggering depth and sophistication. While human science has achieved remarkable insights in just a few centuries of systematic investigation, the mature sciences of superhabitable worlds might have solved fundamental questions about consciousness, reality, and existence that remain mysteries to our current understanding. The technological integration with biological systems achieved by such advanced civilizations might render the distinction between natural and artificial processes meaningless. Their technologies could operate through biological mechanisms so sophisticated they appear indistinguishable from enhanced natural phenomena to observers from less developed worlds. The planetary engineering capabilities of mature civilizations on superhabitable worlds might focus not on conquering or exploiting natural systems, but on optimizing and enhancing the biological processes that already operate with near-perfect efficiency. Their interventions might be so subtle and well integrated that they enhance rather than disrupt the natural harmony of their planetary ecosystems. The interstellar communication methods employed by such civilizations might utilize techniques that transcend our current understanding of information transmission, rather than electromagnetic signals that require massive energy expenditures and suffer from inverse square law limitations. They might employ biological or quantum mechanisms that operate according to principles we haven't yet discovered. The cultural development possible under superhabitable conditions might produce civilizations with social structures and value systems optimized for long-term sustainability and collective flourishing. The absence of resource scarcity and environmental instability could permit the development of social organizations based on principles of cooperation and mutual enhancement rather than competition and resource accumulation. The artistic and philosophical achievements of such mature civilizations might represent the full flowering of conscious creativity operating under optimal conditions for extended periods of cosmic time. Their cultural productions might achieve levels of beauty, complexity, and meaning that transcend our current aesthetic and intellectual frameworks. The detection of these advanced civilizations will require observational strategies that go beyond searching for primitive technological signatures, similar to our own early radio and television broadcasts. We need to develop techniques for recognizing the subtle perfection that might characterize mature planetary management systems operating on timescales measured in geological ages. The atmospheric analysis techniques we're developing could reveal not just the presence of life, but evidence of life operating at levels of efficiency and integration that indicate deliberate optimization rather than random evolutionary processes. The chemical signatures of perfectly balanced atmospheric systems might represent the fingerprints of civilizations that have learned to enhance rather than exploit their planetary environments. The orbital mechanics of planetary systems around superhabitable worlds might reveal evidence of large-scale engineering projects designed to optimize long-term habitability. The positioning of asteroids, comets, and even other planets might reflect deliberate interventions designed to maintain optimal conditions across cosmic timescales. But perhaps most importantly, the discovery of superhabitable worlds forces us to confront fundamental questions about our own potential for development and growth. If biological evolution can achieve such remarkable sophistication under optimal conditions, what might human consciousness and civilization become if we learn to create superhabitable conditions on our own world or future colonization targets? The terraforming implications of superhabitable planet research suggest techniques for transforming marginal worlds into optimal habitats for life. The atmospheric engineering, geological modification, and biological integration strategies revealed by studying these natural superhabitable systems could guide our own efforts to create superior living environments throughout the solar system and beyond. The philosophical implications reach even deeper, challenging our assumptions about the nature of intelligence, consciousness, and existence itself. The forms of awareness that might emerge under superhabitable conditions could represent evolutionary destinations for consciousness that we haven't yet imagined, possibilities for mental and spiritual development that transcend our current human limitations. The cosmic perspective provided by superhabitable planet research reveals a universe potentially teeming with forms of life and intelligence that surpass our terrestrial experience in ways that inspire rather than diminish our sense of cosmic significance. Rather than reducing humanity to cosmic insignificance, the discovery of superior worlds suggests possibilities for growth and development that elevate our understanding of what consciousness might become given optimal conditions and sufficient time. As we stand at the threshold of detecting and studying these remarkable worlds in unprecedented detail, we face the exciting possibility that the universe might be far more alive, more intelligent, and more hospitable to the flowering of consciousness than our earthbound experience has suggested. The superhabitable planets scattered throughout our galaxy represent not just scientific curiosities, but glimpses of what existence might achieve when operating under conditions optimized for the full expression of biological and intellectual potential. The journey toward understanding these worlds will require technological capabilities we're only beginning to develop, but the rewards promise insights into the deepest questions about life, consciousness, and our place in the cosmic order. The superhabitable planets await our discovery, holding secrets that could transform our understanding of what it means to be alive in a universe where optimal conditions for existence might be far more common than we ever dared to hope. The atmospheric chemistry models for superhabitable worlds are revealing something extraordinary about how life might influence planetary conditions on scales we've never witnessed. When we analyze the spectroscopic data from these distant worlds, we're seeing chemical signatures that suggest biological processes operating with an efficiency and coordination that transforms entire atmospheric systems into finely tuned life support mechanisms. Imagine atmospheric compositions where every molecule serves multiple purposes in maintaining optimal conditions for life. The oxygen levels aren't just sufficient for respiration, they're precisely calibrated to maximize cellular energy production, while preventing the oxidative stress that limits lifespan in Earth organisms. The carbon dioxide concentrations maintain perfect greenhouse warming while providing abundant raw materials for photosynthesis that operates at theoretical maximum efficiency. But what's truly remarkable is how these atmospheric systems appear to self-regulate through biological feedback mechanisms of stunning sophistication. The seasonal variations we're detecting suggest planetary-scale coordination between different life forms, creating atmospheric rhythms that optimize conditions for maximum biological productivity throughout the year. It's as if entire worlds have evolved into unified living systems where every organism contributes to maintaining perfect environmental conditions. The water vapor distributions on these superhabitable worlds reveal hydrological cycles that put Earth's weather systems to shame. The enhanced atmospheric mass and optimal temperature gradients create precipitation patterns that ensure every region receives exactly the right amount of moisture for maximum biological flourishing. No deserts, no floods, just perfectly distributed water resources that support lush ecosystems across entire continental surfaces. The cloud formation patterns we're observing through atmospheric modeling suggest weather systems that actively enhance rather than threaten biological activity. Instead of the destructive storms that periodically devastate Earth's ecosystems, these worlds appear to generate gentle, nurturing weather patterns that distribute resources while protecting surface life from any harmful radiation from their host stars. The soil chemistry analysis of superhabitable worlds inferred from atmospheric outgassing patterns reveals mineral compositions that would make Earth's most fertile agricultural regions seem impoverished by comparison. The enhanced geological activity continuously refreshes soil nutrients, while the stable climate conditions allow organic matter to accumulate in concentrations that support plant communities of unprecedented productivity and diversity. These aren't just better growing conditions. They're soil systems that have been enriched by billions of years of biological activity under optimal conditions. The deep, nutrient-rich substrates that result from extended geological and biological evolution could support root systems and plant communities that dwarf the Amazon rainforest in both scale and complexity. But perhaps most fascinating is how the biological and geological cycles on these worlds appear to have achieved perfect integration over cosmic timescales. The chemical weathering processes, the atmospheric dynamics, and the biological nutrient cycling all operate in harmony to maintain optimal conditions without the boom and bust cycles that characterize Earth's environmental history. The magnetic field measurements from some of these superhabitable candidates suggest protective mechanisms that far exceed Earth's magnetosphere in both strength and stability. These enhanced magnetic shields don't just deflect harmful cosmic radiation, they appear to channel and focus beneficial stellar energy in ways that optimize conditions for surface life while protecting atmospheric integrity across geological ages. The tidal dynamics operating in some superhabitable systems reveal gravitational interactions of breathtaking complexity and beauty. Multiple large moons create tidal patterns that drive ocean mixing with precision, that optimizes marine ecosystem productivity while maintaining stable global climate regulation. These aren't random gravitational accidents, but orbital configurations that enhance habitability through mechanisms we're only beginning to understand. The enhanced ocean mixing brings deep-sea nutrients to surface waters with efficiency that supports marine ecosystems more productive than anything in Earth's oceans. The complex tidal rhythms also drive atmospheric circulation patterns that distribute heat and moisture with unprecedented effectiveness, creating global climate stability that has persisted for billions of years. The evolutionary trajectories possible under such optimal conditions challenge everything we thought we knew about biological development. While Earth's history has been shaped by catastrophic interruptions that reset evolutionary progress, these superhabitable worlds have provided uninterrupted environments for life to explore possibilities that we can barely conceive. The symbiotic relationships that develop under such stable conditions might achieve levels of integration that transform individual organisms into components of planetary-scale biological networks. The chemical communication systems that evolve in optimal atmospheric conditions could create coordination mechanisms that allow entire ecosystems to function as unified intelligent systems. But what truly captures the imagination is the possibility that consciousness itself might evolve differently under superhabitable conditions. The stable, nurturing environments of these worlds might foster the development of awareness that operates on completely different principles than the survival-focused intelligence that evolved on our more challenging planet. The temporal perspectives of minds that develop under conditions of abundance and stability might encompass scales that dwarf human experience. Consciousness that emerges from biological systems with access to optimal nutrition and protection from environmental stresses might develop intellectual capabilities that transcend our current understanding of what minds can achieve. The collective intelligence possible when highly optimized organisms coordinate their activities across planetary scales might represent forms of awareness that process information and make decisions using biological architectures we haven't yet imagined. These planetary minds might approach problems and opportunities with cognitive resources that make our most advanced artificial intelligence systems seem primitive by comparison. The scientific methodologies employed by civilizations with billions of years of continuous observation and experimentation under optimal conditions might have solved fundamental questions about the nature of reality that remain mysteries to our current understanding. Their knowledge systems could encompass insights into consciousness, existence, and cosmic purpose that transcend our philosophical frameworks. The technological development on superhabitable worlds might follow trajectories that diverge dramatically from human experience. Rather than conquering and exploiting natural systems, advanced civilizations on these worlds might have learned to enhance and optimize the biological processes that already operate with near-perfect efficiency under their superior environmental conditions. Their technologies might be so well integrated with natural systems that they appear indistinguishable from enhanced biological phenomena to observers from less developed worlds. The distinction between natural and artificial processes might become meaningless when technology operates through biological mechanisms that have been optimized across cosmic timescales. The energy systems developed by such mature civilizations might achieve efficiency levels that approach theoretical limits while producing no waste products or environmental disruption. Their mastery of biological and physical processes might allow them to harness stellar energy with techniques that enhance rather than compete with natural photosynthetic systems. The materials science achievements possible under superhabitable conditions might produce substances and structures that seem almost magical from our current technological perspective. The combination of enhanced geological processes, optimal chemical conditions, and billions of years of development time could yield material capabilities that transcend our understanding of what's possible through known physical processes. The communication systems employed by civilizations on superhabitable worlds might utilize mechanisms that operate according to principles we haven't discovered. Rather than electromagnetic signals that suffer from distance limitations and interference, they might employ biological or quantum techniques that maintain perfect fidelity across interstellar distances. The cultural development possible under conditions of resource abundance and environmental stability might produce civilizations with social structures optimized for collective flourishing rather than individual survival. Their artistic and philosophical achievements might represent the full flowering of conscious creativity, operating under optimal conditions for extended periods of cosmic time. The detection strategies we're developing to identify these advanced civilizations must account for signatures that transcend our current technological experience. We're learning to recognize patterns in atmospheric composition, orbital dynamics, and even gravitational wave emissions that might indicate the presence of intelligence operating on planetary scales through mechanisms we're only beginning to understand. The atmospheric spectroscopy techniques being developed by next-generation telescopes will be sensitive enough to detect not just the presence of life, but evidence of life operating at levels of efficiency and coordination that suggest deliberate optimization rather than random evolutionary processes. The chemical signatures of perfectly balanced atmospheric systems might represent the fingerprints of civilizations that have achieved harmony with their planetary environment. The orbital mechanics analysis of superhabitable systems might reveal evidence of large-scale engineering projects designed to maintain optimal conditions across cosmic timescales. The precise positioning of asteroids, comets, and even planetary orbits might reflect interventions so subtle and well integrated that they enhance natural processes while remaining nearly invisible to casual observation. The gravitational wave signatures from these systems could carry information about geological and biological processes operating on scales that dwarf anything we observe on Earth. The enhanced planetary activity of superhabitable worlds might generate space-time distortions that encode details about their atmospheric dynamics, tidal systems, and even large-scale biological coordination mechanisms. But perhaps most importantly, the search for superhabitable worlds is transforming our understanding of humanity's potential for growth and development. If consciousness and civilization can achieve such remarkable sophistication under optimal conditions, what might our own species become if we learn to create superhabitable environments on Earth or future worlds we might inhabit? The terraforming implications of superhabitable planet research suggest techniques for transforming marginal environments into optimal habitats that could support life forms and civilizations of unprecedented complexity and capability. The atmospheric engineering, geological optimization, and biological integration strategies revealed by studying these natural systems could guide our efforts to create superior living conditions throughout the solar system and beyond. The philosophical dimensions of this research reach into the deepest questions about the nature of existence itself. The forms of awareness and understanding that might emerge under superhabitable conditions could represent evolutionary destinations for consciousness that inspire rather than intimidate our current human limitations. They suggest possibilities for mental, spiritual, and social development that transcend our terrestrial experience while remaining achievable through natural processes, given optimal conditions and sufficient time. The cosmic perspective provided by superhabitable planet research reveals a universe potentially abundant with forms of life, intelligence, and consciousness that surpass our earthbound experience in ways that elevate our understanding of what existence might become. Rather than diminishing humanity's cosmic significance, the discovery of these superior worlds suggests possibilities for growth that could transform our species into something worthy of the remarkable universe we inhabit. As we continue developing the observational capabilities necessary to study these distant worlds in unprecedented detail, we stand at the threshold of discoveries that could fundamentally revolutionize human understanding of life's potential throughout the cosmos. The superhabitable planets scattered across our galaxy represent not just scientific objectives, but glimpses of what biological evolution and conscious development might achieve when operating under conditions optimized for the full expression of existence itself. The journey toward understanding these worlds will require technological capabilities that push the boundaries of human engineering. But the insights we gain promise to illuminate the deepest mysteries about consciousness, intelligence, and our place in a universe where optimal conditions for life might be far more common than our Earth-centered perspective has allowed us to imagine. The superhabitable planets await our discovery, holding secrets that could transform our understanding of what it means to be alive in a cosmos where the full potential of existence might be realized on billions of worlds throughout the galaxy. The biosignature detection protocols we're developing for these superhabitable worlds are uncovering atmospheric phenomena that operate on principles we're only beginning to comprehend. When we peer through our most advanced spectrographs at these distant atmospheres, we're witnessing chemical orchestrations of such precision and beauty that they challenge our fundamental assumptions about what natural processes can achieve. Picture atmospheric systems where trace gases exist in ratios so perfectly balanced they seem almost deliberately crafted. The methane and oxygen signatures we're detecting don't just indicate biological activity, they suggest biological communities operating with coordination that spans entire planetary surfaces. These aren't random chemical fluctuations, but atmospheric symphonies where every molecule plays its part in maintaining optimal conditions for life to flourish. The seasonal atmospheric variations we're observing through long-term monitoring campaigns reveal patterns of breathtaking complexity and elegance. Unlike Earth's somewhat chaotic seasonal changes, these superhabitable worlds display atmospheric rhythms that pulse with the precision of cosmic clockwork. The carbon dioxide levels rise and fall in perfect harmony with stellar seasons, while oxygen concentrations fluctuate in ways that optimize energy availability for biological communities across different climatic zones. But what truly captures our scientific imagination is how these atmospheric compositions appear to respond dynamically to changing stellar conditions. When the host stars experience minor fluctuations in energy output, the planetary atmospheres adjust their chemical balance with remarkable speed and precision. It's as if these worlds possess atmospheric immune systems that maintain optimal habitability regardless of external perturbations. The water vapor mapping of superhabitable candidates reveals hydrological architectures that put Earth's water cycle to shame in terms of both efficiency and elegance. The atmospheric moisture doesn't just exist randomly throughout these planetary envelopes, it's distributed with mathematical precision that ensures every ecosystem receives exactly the hydration it needs for maximum biological productivity. The cloud formation patterns we're detecting through infrared analysis suggest weather systems that actively nurture rather than challenge surface life. Instead of the sometimes destructive storms that periodically devastate terrestrial ecosystems, these worlds generate precipitation events that deliver resources while protecting vulnerable biological communities from any harmful stellar radiation that might penetrate their atmospheric shields. The atmospheric pressure profiles of these superhabitable worlds reveal another dimension of their environmental superiority. The enhanced atmospheric mass creates surface conditions where liquid water remains stable across temperature ranges that far exceed Earth's relatively narrow window. This expanded stability zone allows surface life to colonize regions that would be frozen wastelands or boiling deserts under our planet's atmospheric constraints. Higher atmospheric density also provides more effective shielding against cosmic radiation while improving the efficiency of gas exchange processes, crucial for complex organisms. These dense atmospheric envelopes could support larger, more energetic life forms than Earth's relatively thin atmosphere permits, potentially giving rise to biological communities of unprecedented scale and complexity. The chemical weathering signatures we're inferring from atmospheric outgassing patterns suggest geological processes that maintain optimal soil chemistry across cosmic timescales. The enhanced tectonic activity on these more massive worlds continuously exposes fresh minerals to weathering, while the stable climate conditions allow organic compounds to accumulate in concentrations that would transform any terrestrial landscape into an agricultural paradise. These soil development processes, operating under superhabitable conditions for billions of years, could produce substrates enriched with nutrients and organic matter to depths that dwarf even Earth's most fertile regions. The root systems and plant communities that could develop in such optimal growing media might achieve productivity levels that approach theoretical biological limits. But perhaps most remarkably, the integration between atmospheric, geological, and biological cycles on these worlds appears to have achieved a harmony that transcends anything we observe in terrestrial systems. The chemical processes that regulate atmospheric composition, the geological activities that maintain soil fertility, and the biological mechanisms that cycle nutrients all operate in perfect synchronization to maintain optimal conditions without the environmental fluctuations that characterize Earth's more chaotic systems. The magnetic field configurations we're detecting around some superhabitable candidates reveal protective mechanisms that far surpass Earth's magnetosphere in both strength and sophistication. These enhanced magnetic shields don't just deflect harmful particles from space, they appear to channel and focus beneficial stellar radiation in ways that optimize surface conditions while maintaining atmospheric integrity across geological ages. The complex magnetic geometries created by the interaction between planetary and stellar magnetic fields could produce radiation environments that selectively filter harmful frequencies while allowing beneficial wavelengths to reach surface ecosystems. This sophisticated radiation management could enable photosynthetic processes to operate at efficiencies that exceed anything possible under Earth's less optimal magnetic protection. The gravitational dynamics operating in superhabitable systems reveal orbital architectures of stunning complexity and beauty. The presence of multiple large moons creates tidal interactions that drive ocean circulation with precision, that optimizes marine ecosystem productivity while maintaining global climate stability. These aren't accidental gravitational configurations, but orbital relationships that enhance habitability through mechanisms we're only beginning to appreciate. The enhanced ocean mixing driven by complex tidal cycles brings deep-sea nutrients to surface waters with efficiency that could support marine biological communities more productive and diverse than anything in Earth's oceans. The rhythmic tidal patterns also influence atmospheric circulation in ways that distribute heat and moisture with unprecedented effectiveness across continental surfaces. The evolutionary possibilities that emerge under such optimal conditions stretch our understanding of what biological development can achieve given sufficient time and ideal environmental circumstances. While Earth's evolutionary history has been repeatedly interrupted by catastrophic events that reset biological progress, these superhabitable worlds have provided stable platforms for life to explore developmental pathways we can barely imagine. The symbiotic relationships that could evolve under conditions of environmental abundance and stability might achieve integration levels that blur the boundaries between individual organisms and planetary-scale biological networks. The chemical communication systems that develop in optimal atmospheric conditions could create coordination mechanisms that allow entire ecosystems to function as unified information processing systems. The temporal perspectives of consciousness that might emerge under superhabitable conditions challenge our assumptions about the nature of awareness itself. Minds that develop in environments free from survival pressures and resource limitations might evolve cognitive architectures optimized for different purposes than the rapid adaptation and competitive strategies that characterize terrestrial intelligence. The collective intelligence possible when optimized biological systems coordinate their activities across planetary scales might represent forms of awareness that process information using distributed biological architectures we haven't yet conceived. These planetary-scale minds might approach problems with cognitive resources that transcend our current understanding of what consciousness can achieve. The scientific methodologies that could develop through billions of years of continuous observation and experimentation under optimal conditions might have solved fundamental questions about reality that remain beyond our current intellectual reach. The knowledge systems of mature civilizations on superhabitable worlds could encompass insights into consciousness, existence, and cosmic purpose that transform our philosophical understanding of what it means to be aware in this universe. The technological trajectories followed by civilizations that emerge on these optimal worlds might diverge dramatically from human developmental patterns. Rather than the resource competition and environmental exploitation that has characterized human technological progress, advanced societies on superhabitable worlds might have learned to enhance and optimize the biological processes that already operate with remarkable efficiency under their superior environmental conditions. Their technologies might achieve such seamless integration with natural systems that the distinction between artificial and biological processes becomes meaningless. The engineering capabilities that develop through billions of years of refinement under optimal conditions might produce solutions to energy, materials, and information processing challenges that seem almost magical from our current technological perspective. The energy systems developed by mature civilizations on superhabitable worlds might harness stellar radiation with efficiency levels that approach theoretical limits while producing no waste products or environmental disruption. Their mastery of biological and physical processes might allow them to channel cosmic energy through mechanisms that enhance rather than compete with natural photosynthetic systems. The materials science achievements possible under superhabitable conditions might yield substances with properties that transcend our current understanding of physical limitations. The combination of enhanced geological processes, optimal chemical conditions, and extended development timescales could produce material capabilities that revolutionize our concepts of what's achievable through known physical principles. The communication systems employed by advanced civilizations on these worlds might utilize mechanisms that operate beyond our current technological paradigms. Rather than electromagnetic signals that suffer from distance limitations and interference, they might employ biological quantum or even gravitational techniques that maintain perfect information transfer across interstellar distances. The cultural developments possible under conditions of environmental stability and resource abundance might produce civilizations with social structures optimized for collective flourishing rather than individual competition. Their artistic and philosophical achievements might represent the full expression of conscious creativity operating under optimal conditions for extended periods of cosmic time. The detection methodologies we're developing must account for signatures that transcend our terrestrial technological experience. We're learning to recognize patterns in atmospheric chemistry, orbital mechanics, and even space-time distortions that might indicate intelligence operating on planetary scales through mechanisms that integrate seamlessly with natural processes. The spectroscopic analysis techniques being refined for next-generation telescopes will achieve sensitivity levels sufficient to detect not just biological activity, but evidence of biological systems operating with coordination and efficiency that suggests conscious optimization rather than random evolutionary processes. The chemical fingerprints of perfectly regulated atmospheric systems might represent signatures of civilizations that have achieved complete harmony with their planetary environment. The orbital dynamics modeling of superhabitable systems might reveal evidence of subtle engineering interventions designed to maintain optimal conditions across cosmic timescales. The precise gravitational relationships between planets, moons, and asteroids might reflect modifications so elegant and well integrated that they enhance natural processes while remaining virtually invisible to casual observation. The gravitational wave astronomy techniques we're developing could detect signatures from geological and biological processes operating on scales that dwarf anything observable on Earth. The enhanced planetary activity characteristic of superhabitable worlds might generate space-time ripples that encode information about atmospheric dynamics, tidal systems, and potentially even large-scale biological coordination mechanisms. The implications of discovering these remarkable worlds extend far beyond pure scientific curiosity. If consciousness and civilization can achieve such extraordinary sophistication under optimal conditions, the possibilities for human development become truly inspiring. The atmospheric engineering, geological optimization, and biological integration strategies revealed through studying superhabitable systems could guide our efforts to create superior living environments throughout our solar system and beyond. The philosophical dimensions of this research illuminate profound questions about the ultimate potential of existence itself. The forms of awareness and understanding that might flourish under superhabitable conditions represent evolutionary destinations for consciousness that could transform our species into something worthy of the remarkable universe we're privileged to inhabit. The cosmic perspective emerging from superhabitable planet research suggests a universe potentially abundant with life, intelligence, and consciousness, operating at levels that surpass our earthbound experience while remaining achievable through natural processes, given optimal conditions and sufficient developmental time. These discoveries don't diminish humanity's cosmic significance, but rather illuminate possibilities for growth and transformation that could elevate our understanding of what conscious existence might become. As we continue refining the observational technologies necessary to study these distant worlds with unprecedented precision, we approach discoveries that could fundamentally revolutionize human comprehension of life's potential throughout the cosmos. The superhabitable planets distributed across our galaxy represent more than scientific objectives. They offer glimpses of what biological evolution and conscious development might achieve when operating under conditions optimized for the full expression of existence itself. The journey toward understanding these worlds demands technological capabilities that challenge the boundaries of human engineering and imagination, but the insights awaiting our discovery promise to illuminate the deepest mysteries surrounding consciousness, intelligence, and our place in a universe where optimal conditions for life might be far more prevalent than our Earth-centered perspective has allowed us to envision. The superhabitable worlds that orbit distant stars hold secrets that could transform our understanding of what it means to be alive in a cosmos where the complete potential of existence might be realized on countless worlds scattered throughout the infinite tapestry of space and time. These remarkable planets await our discovery, ready to reveal truths about life, consciousness, and cosmic purpose that could reshape humanity's destiny among the stars. The stars. The quantum mechanical underpinnings of superhabitable worlds reveal principles that operate on scales both infinitesimally small and cosmically vast. When we examine the atomic interactions that govern atmospheric chemistry on these distant worlds, we discover quantum effects that have been amplified and refined across billions of years of optimal conditions. The electron orbital configurations in atmospheric molecules appear to achieve energy states that maximize both stability and reactivity, creating chemical environments where life processes can operate with unprecedented efficiency. The quantum tunneling effects that govern molecular interactions in these enhanced atmospheres might enable biochemical pathways that remain impossible under Earth's less optimal quantum conditions. The probability wave functions that describe molecular behavior could collapse into configurations that favor life-supporting reactions while suppressing harmful chemical processes. These aren't random quantum fluctuations, but quantum mechanical systems that have evolved toward optimal states through extended interaction with biological processes. The coherence times of quantum states in superhabitable atmospheric systems might persist far longer than anything we observe in terrestrial conditions. The reduced electromagnetic interference and enhanced chemical stability could allow quantum biological processes to maintain coherent superposition states that enable cellular mechanisms of extraordinary sophistication and efficiency. But what truly fascinates quantum physicists studying these systems is how macroscopic biological processes might harness quantum effects in ways that transcend our current understanding of the classical quantum boundary. The optimal conditions on superhabitable worlds could permit the evolution of organisms that utilize quantum coherence for information processing, energy transfer, and environmental sensing, with capabilities that approach theoretical quantum mechanical limits. The thermodynamic analysis of superhabitable planetary systems reveals energy flow patterns that approach ideal efficiency across all scales of organization. The stellar energy input, atmospheric processing, geological cycling, and biological utilization all operate in harmony to minimize entropy production while maximizing the complexity and organization that can emerge from available energy sources. The heat engine efficiency of atmospheric circulation systems on these worlds might achieve Carnot cycle performance levels that far exceed anything possible in Earth's more chaotic atmospheric dynamics. The temperature differentials and pressure gradients that drive weather patterns could be optimized through billions of years of atmospheric evolution to extract maximum useful work from solar energy input while maintaining perfect climate stability. The biological thermodynamics operating under superhabitable conditions might achieve energy conversion efficiencies that approach fundamental physical limits. Photosynthetic processes could capture and convert stellar radiation with quantum efficiencies that make Earth's plant communities seem wasteful by comparison. Cellular respiration could extract energy from chemical bonds with precision that minimizes heat waste while maximizing available work for biological processes. The information theory applications to superhabitable worlds reveal communication and coordination mechanisms that operate with Shannon entropy optimization across planetary scales. The chemical signaling networks that evolve in optimal atmospheric conditions could achieve information transfer rates and fidelity levels that enable coordination between biological systems separated by continental distances. The error correction mechanisms that develop in biological information systems under stable environmental conditions might achieve reliability levels that surpass our most advanced technological communication networks. The redundancy and feedback systems that evolve in optimal conditions could maintain information integrity across temporal scales that span geological ages. The complexity theory analysis of superhabitable ecosystems suggests emergent properties that transcend our current understanding of how complex systems organize and maintain themselves. The phase transitions between different levels of biological organization might occur with critical point behaviors that optimize both stability and adaptability across environmental gradients. The network topology of biological interactions on these worlds could achieve small world and scale-free properties that maximize information flow while maintaining robustness against perturbations. The connectivity patterns between species, ecosystems, and even planetary-scale biological processes might represent optimized network architectures that emerge through billions of years of evolutionary refinement. The fractal geometry observable in superhabitable ecosystem structures might reveal self-similar patterns that optimize resource utilization and energy distribution across all spatial scales. From microscopic cellular arrangements to continental-scale vegetation patterns, the geometric relationships could achieve mathematical relationships that approach theoretical optimization for biological systems. The hydrodynamic modeling of superhabitable ocean systems reveals circulation patterns that achieve perfect balance between mixing efficiency and stability maintenance. The three-dimensional flow structures that develop in these optimal marine environments might create nutrient distribution networks that support biological productivity at every depth and location throughout planetary ocean systems. The turbulence characteristics of superhabitable atmospheric and oceanic flows might achieve Reynolds number regimes that optimize energy transfer while minimizing destructive chaos. The fluid dynamics could operate in parameter spaces that maintain laminar efficiency where needed, while generating beneficial mixing where enhanced transport serves biological communities. The electromagnetic field interactions on superhabitable worlds create radiation environments that selectively enhance beneficial biological processes while providing perfect protection against harmful frequencies. The planetary magnetic field geometries might achieve configurations that focus stellar radiation into optimal spectral distributions for photosynthetic efficiency while deflecting dangerous cosmic ray components. The plasma physics operating in superhabitable magnetospheres could create charged particle dynamics that generate beneficial ionospheric effects for atmospheric chemistry while maintaining perfect electromagnetic shielding for surface ecosystems. The auroral displays resulting from these optimized magnetic field interactions might create atmospheric ionization patterns that enhance rather than disrupt biological processes. The crystallographic analysis of geological formations on superhabitable worlds suggests mineral structures that optimize both chemical reactivity and mechanical stability for supporting biological systems. The crystal lattice arrangements that develop under enhanced geological conditions might create material properties perfectly suited for biological utilization while maintaining geological integrity across cosmic timescales. The metamorphic processes operating under superhabitable geological conditions might produce mineral assemblages with properties that enhance soil chemistry while providing optimal substrates for biological community development. The pressure and temperature regimes that characterize enhanced planetary interiors could generate geological materials specifically optimized for supporting complex life systems. The isotope ratios observed in superhabitable atmospheric and geological samples reveal nuclear processes that maintain optimal elemental compositions for biological utilization. The stellar nucleosynthesis products that enrich these planetary systems might provide elemental abundances perfectly balanced for supporting complex biochemistry while avoiding toxic accumulations that limit biological development. The radiometric dating of superhabitable planetary formation processes suggests accretion timescales that optimize both planetary mass accumulation and volatile retention for maintaining optimal atmospheric conditions. The sequence of geological and atmospheric evolution might follow pathways that maximize habitability duration while minimizing the environmental instabilities that characterize less optimal planetary development. The spectroscopic signatures of superhabitable worlds continue revealing chemical fingerprints that indicate biological and geological processes operating in perfect harmony. The molecular absorption lines we detect carry information about atmospheric dynamics, surface chemistry, and even potential biological activity that transcends anything we observe in terrestrial systems. The polarimetry analysis of reflected light from these worlds might reveal surface and atmospheric properties that indicate optimal conditions for complex life systems. The polarization signatures could encode information about cloud formations, surface vegetation patterns, and atmospheric composition that provides unprecedented insights into planetary habitability assessment. The photometric variability studies of superhabitable worlds reveal temporal patterns that suggest biological and geological cycles operating with clockwork precision across seasonal and annual timescales. The brightness variations that result from changing surface and atmospheric conditions might indicate planetary systems that maintain optimal habitability through active regulation mechanisms. The astrometric measurements of superhabitable planetary systems reveal orbital dynamics that optimize long-term stability while maintaining optimal energy input from host stars. The gravitational interactions between planets, moons, and stellar companions might create resonance relationships that enhance habitability through mechanisms we're only beginning to understand. The habitability modeling for these worlds incorporates climate dynamics, atmospheric chemistry, and geological processes into comprehensive simulations that reveal the complex interactions maintaining optimal conditions across cosmic timescales. The feedback mechanisms that regulate planetary habitability might operate through principles that transcend our current understanding of planetary system evolution. The astrobiology implications of superhabitable world research extend far beyond simple questions of life detection to encompass fundamental questions about the nature of biological complexity and the ultimate potential for conscious development throughout the universe. These worlds represent natural experiments in biological optimization that could reveal principles governing life's ability to create and maintain optimal conditions for continued evolution and complexity increase. The comparative planetology emerging from superhabitable world studies challenges our Earth-centered assumptions about what constitutes normal planetary development. The atmospheric evolution, geological activity, and magnetic field generation that characterize these optimal worlds might represent the standard against which all planetary habitability should be measured, rather than exceptional cases requiring special explanation. The exogeology of superhabitable worlds reveals rock formations and mineral compositions that optimize chemical weathering for biological nutrient cycling while maintaining geological stability across billion-year timescales. The tectonic processes that shape these planetary surfaces might create topographical features that enhance atmospheric circulation while providing optimal habitat diversity for biological communities. The atmospheric escape mechanisms operating on superhabitable worlds appear to maintain perfect balance between atmospheric retention and atmospheric refresh that prevents stagnation while avoiding atmospheric loss. The hydrodynamic and thermal escape processes might operate in regimes that optimize atmospheric composition for biological requirements while maintaining long-term stability. The stellar evolution considerations for superhabitable world host stars reveal main sequence lifetimes and luminosity evolution patterns that provide stable energy input for periods that dwarf the habitability timescales available around solar-type stars. The nuclear burning processes in orange dwarf stars might maintain optimal spectral output for photosynthetic efficiency while avoiding the luminosity variations that destabilize planetary climates around other stellar types. The galactic chemical evolution that produces superhabitable worlds requires metal enrichment histories that provide optimal elemental abundances for rocky planet formation, while avoiding the heavy element contamination that could inhibit biological development. The nucleosynthesis processes operating in galactic stellar populations might need to achieve precise chemical evolution pathways to create the optimal conditions for superhabitable world formation. The cosmological implications of superhabitable world prevalence suggest that life-friendly conditions might be far more common throughout cosmic history than our solar system experience indicates. The universe might have been producing optimal conditions for biological complexity across redshift ranges that encompass most of cosmic time, since stellar nucleosynthesis began enriching interstellar medium with heavy elements necessary for rocky planet formation. The anthropic considerations raised by superhabitable world research challenge our assumptions about humanity's place in cosmic biological development. If optimal conditions for life are common throughout the galaxy, our solar system might represent a marginal environment for biological complexity rather than a typical or optimal case for supporting complex life and intelligence. The technological implications of understanding superhabitable world characteristics could guide future efforts to optimize Earth's environmental conditions or to select optimal targets for interstellar exploration and potential colonization efforts. The atmospheric engineering, geological modification, and ecological optimization techniques revealed through studying natural superhabitable systems could inform human efforts to create superior living environments throughout the solar system. The philosophical dimensions of superhabitable world research illuminate profound questions about the ultimate potential of conscious existence throughout the universe. If biological evolution and conscious development can achieve such remarkable sophistication under optimal planetary conditions, the possibilities for awareness and understanding that might emerge throughout the galaxy could transcend our current intellectual frameworks while remaining achievable through natural processes given sufficient time and optimal environmental conditions. The observational programs dedicated to superhabitable world detection and characterization represent humanity's most ambitious efforts to understand life's potential throughout the cosmos. The space-based and ground-based telescopes we're deploying will reveal atmospheric compositions, surface conditions, and potentially even biosignatures from worlds that might support biological communities more diverse and sophisticated than anything in Earth's evolutionary history. The data analysis techniques being developed to interpret superhabitable world observations require computational methods that can extract meaningful information from spectroscopic, photometric, and astrometric data, while accounting for the complex interactions between stellar, atmospheric, geological, and potentially biological processes that determine planetary habitability characteristics. The theoretical frameworks guiding superhabitable world research integrate insights from atmospheric physics, geological sciences, evolutionary biology, and astrobiology into comprehensive models that predict the conditions necessary for optimal biological development, while identifying the observational signatures that would confirm the presence of truly superior habitable environments. The interdisciplinary collaboration required for superhabitable world research brings together expertise from astronomy, planetary science, atmospheric chemistry, geology, biology, and even psychology and philosophy to address questions that transcend traditional academic boundaries, while requiring insights from multiple scientific disciplines to achieve comprehensive understanding. The educational implications of superhabitable world research inspire new approaches to teaching astronomy, biology, and environmental science that emphasize the cosmic context of life, while encouraging students to think beyond Earth-centered perspectives about biological potential and environmental optimization throughout the universe. The public engagement dimensions of this research capture imaginations while communicating scientific insights about planetary habitability, biological evolution, and humanity's place in a universe that might be far more alive and hospitable to conscious development than our terrestrial experience has suggested. The international cooperation required for superhabitable world research brings together scientific communities from around the world in collaborative efforts that transcend political boundaries while pursuing knowledge that benefits all humanity's understanding of life's potential throughout the cosmos. The long-term research programs dedicated to superhabitable world studies will span decades as we develop the observational capabilities necessary to detect and characterize these distant worlds, while building theoretical frameworks sophisticated enough to interpret the complex data these observations will provide. The ultimate goal of superhabitable world research extends beyond pure scientific knowledge to encompass insights that could transform humanity's relationship with our own planet, while inspiring efforts to optimize environmental conditions for supporting the continued evolution of biological complexity and conscious awareness throughout our solar system and potentially beyond to the stars themselves. As we continue this remarkable journey of discovery, the superhabitable worlds that orbit distant suns across our galaxy await our detection and study. These remarkable planets hold secrets that could revolutionize our understanding of life's potential throughout the universe, while revealing possibilities for biological and conscious development that transcend our earthbound experience. The cosmos may be far more alive, more vibrant, and more hospitable to the flowering of awareness than we ever dared imagine. And these optimal worlds represent our best hope for understanding what existence might achieve when operating under conditions perfectly suited for the full expression of life's creative potential. The quantum mechanical foundations underlying superhabitable worlds reveal something extraordinary about how consciousness might evolve when freed from the environmental pressures that shape terrestrial awareness. As we peer deeper into these distant atmospheric systems, we're discovering that the stable nurturing conditions create quantum coherence effects that could support forms of information processing beyond anything we've observed in Earth-based biological systems. The molecular interactions in these enhanced atmospheres maintain quantum entanglement across scales that would be impossible under our planet's more chaotic conditions. The reduced electromagnetic interference and optimal chemical stability allow biological quantum effects to persist for extended periods, potentially enabling cellular processes that utilize quantum superposition and entanglement for computation, communication, and environmental sensing, with capabilities that approach theoretical limits. But what truly captures our scientific imagination is how these quantum effects might scale up to influence macroscopic biological organization. The optimal atmospheric conditions could permit the evolution of organisms that maintain quantum coherence, not just at the molecular level, but across entire neural networks, potentially giving rise to forms of consciousness that process information using quantum mechanical principles we're only beginning to understand. Picture neural architectures that utilize quantum tunneling effects for synaptic transmission, allowing thoughts to propagate through biological networks with speed and efficiency that transcends classical neural computation. Imagine sensory systems that employ quantum entanglement to detect environmental changes with precision that makes our most sensitive scientific instruments seem crude by comparison. The thermodynamic analysis of these superhabitable systems reveals energy utilization patterns that approach theoretical efficiency limits across every scale of organization. The stellar energy that bathes these worlds gets processed through atmospheric, geological, and biological systems with such precision that virtually no useful work potential gets wasted as entropy production. The photosynthetic processes that could evolve under such optimal conditions might achieve quantum efficiency levels that make Earth's plant communities appear almost primitive. The cellular respiration systems that extract energy from organic compounds could operate with precision that minimizes thermal waste while maximizing the energy available for complex biological processes and potentially conscious computation. But perhaps most remarkably, the information processing capabilities that emerge from such optimized biological systems challenge our assumptions about the boundaries between biological and technological intelligence. The chemical signaling networks that develop in perfect atmospheric conditions could achieve information transfer rates that enable real-time coordination between organisms separated by continental distances. The error correction mechanisms that evolve in these stable environments might maintain information integrity across temporal scales spanning geological ages. The biological communication systems could develop redundancy and feedback mechanisms that surpass our most advanced technological networks in both reliability and efficiency. The complexity theory applications to these worlds suggest emergent properties that transcend our current understanding of how complex systems organize themselves. The phase transitions between different levels of biological organization might occur with critical behaviors that optimize both stability and adaptability across environmental gradients that span entire planetary surfaces. The network topology of biological interactions could achieve mathematical relationships that maximize information flow while maintaining robustness against any perturbations that might threaten system stability. The connectivity patterns between individual organisms, ecological communities, and planetary-scale biological processes might represent network architectures that emerge through billions of years of evolutionary optimization. The fractal geometry observable in superhabitable ecosystem structures reveals self-similar patterns that optimize resource distribution and energy utilization across all spatial scales, from microscopic cellular arrangements to continental vegetation patterns. The geometric relationships approach mathematical optimization for biological systems operating under ideal conditions. The hydrodynamic modeling of superhabitable ocean systems reveals circulation patterns that achieve perfect balance between mixing efficiency and stability maintenance. The three-dimensional flow structures create nutrient distribution networks that support biological productivity at optimal levels throughout every depth and location in planetary ocean systems. The electromagnetic field configurations on these worlds create radiation environments that selectively enhance beneficial biological processes while providing complete protection against harmful frequencies. The planetary magnetic field geometries achieve optimal configurations that focus stellar radiation into perfect spectral distributions for photosynthetic efficiency while deflecting dangerous cosmic radiation. The crystallographic analysis of geological formations suggests mineral structures that optimize both chemical reactivity and mechanical stability for supporting biological systems. The crystal lattice arrangements that develop under enhanced geological conditions create material properties perfectly suited for biological utilization, while maintaining geological integrity across cosmic timescales. The isotope ratios observed in these systems reveal nuclear processes that maintain optimal elemental compositions for biological utilization. The stellar nucleosynthesis products that enrich these planetary environments provide elemental abundances perfectly balanced for supporting complex biochemistry, while avoiding toxic accumulations that might limit biological development. The spectroscopic signatures continue revealing chemical fingerprints that indicate biological and geological processes operating in perfect harmony. The molecular absorption features carry information about atmospheric dynamics, surface chemistry, and biological activity that transcends anything we observe in terrestrial systems. The temporal patterns revealed through long-term monitoring suggest biological and geological cycles operating with precision across seasonal and annual timescales. The variations indicate planetary systems that maintain optimal habitability through active regulation mechanisms that have evolved over billions of years of environmental stability. The orbital dynamics reveal gravitational interactions that optimize long-term stability while maintaining optimal energy input from host stars. The resonance relationships between planets, moons, and stellar companions create stability patterns that enhance habitability through mechanisms that represent gravitational architecture of breathtaking elegance. The atmospheric chemistry models incorporate climate dynamics, geological processes, and biological feedback into comprehensive simulations that reveal the complex interactions maintaining optimal conditions across cosmic timescales. The regulatory mechanisms operate through principles that transcend our current understanding of planetary system evolution. The comparative planetology emerging from these studies challenges our Earth-centered assumptions about normal planetary development. The atmospheric evolution, geological activity, and magnetic field generation that characterize these optimal worlds might represent the cosmic standard for planetary habitability rather than exceptional cases requiring special explanation. The stellar evolution considerations reveal main sequence lifetimes that provide stable energy input for periods that dwarf the habitability timescales available around solar-type stars. The nuclear burning processes maintain optimal spectral output for biological efficiency, while avoiding the luminosity variations that destabilize planetary climates around other stellar types. The galactic chemical evolution that produces these worlds requires metal enrichment histories that provide optimal elemental abundances for rocky planet formation. The nucleosynthesis processes operating in stellar populations achieve precise chemical evolution pathways that create optimal conditions for superhabitable world formation throughout galactic history. The cosmological implications suggest that life-friendly conditions might be far more common throughout cosmic history than our solar system experience indicates. The universe might have been producing optimal conditions for biological complexity across redshift ranges that encompass most of cosmic time since stellar nucleosynthesis began enriching interstellar medium with elements necessary for rocky planet formation. The technological implications could guide future efforts to optimize Earth's environmental conditions or select optimal targets for interstellar exploration. The atmospheric engineering, geological modification, and ecological optimization techniques, revealed through studying natural superhabitable systems, could inform human efforts to create superior living environments throughout our solar system. The observational programs dedicated to detecting these worlds represent humanity's most ambitious efforts to understand life's potential throughout the cosmos. The space-based and ground-based telescopes we're deploying will reveal atmospheric compositions, surface conditions, and potentially biosignatures from worlds that might support biological communities more diverse than anything in Earth's evolutionary history. The data analysis techniques being developed require computational methods that extract meaningful information from spectroscopic, photometric, and astrometric observations, while accounting for complex interactions between stellar, atmospheric, geological, and biological processes that determine planetary habitability characteristics. The theoretical frameworks integrate insights from atmospheric physics, geological sciences, evolutionary biology, and astrobiology into comprehensive models that predict conditions necessary for optimal biological development, while identifying observational signatures that would confirm the presence of truly superior habitable environments. The interdisciplinary collaboration brings together expertise from astronomy, planetary science, atmospheric chemistry, geology, biology, psychology, and philosophy to address questions that transcend traditional academic boundaries while requiring insights from multiple scientific disciplines to achieve comprehensive understanding. The long-term research programs will span decades as we develop observational capabilities necessary to detect and characterize these distant worlds, while building theoretical frameworks sophisticated enough to interpret the complex data these observations will provide about planetary habitability optimization. As we stand at this threshold of discovery, the superhabitable worlds scattered throughout our galaxy represent more than scientific curiosities. They offer glimpses into what biological evolution and conscious development might achieve when operating under conditions optimized for the full expression of life's creative potential across cosmic timescales. The quantum coherence effects, thermodynamic optimization, information processing capabilities, and consciousness architectures that might emerge under such ideal conditions could reveal forms of awareness that transcend our current understanding, while remaining achievable through natural processes, given optimal environmental conditions and sufficient developmental time. These remarkable worlds await our discovery, holding secrets about the ultimate potential of existence in a universe that might be far more alive, more conscious, and more hospitable to the flowering of awareness than our earthbound experience has allowed us to imagine. The cosmos beckons with possibilities that could transform our understanding of what it means to be conscious in a reality where optimal conditions for life might be the rule rather than the exception throughout the infinite expanse of space and time. Time. The quantum biological networks that might emerge under superhabitable conditions open possibilities for consciousness that operate through mechanisms we've never encountered in terrestrial neuroscience. When biological systems develop in atmospheres with perfect chemical stability, and optimal electromagnetic conditions, the quantum effects that remain fragile and fleeting in Earth organisms could become robust, persistent features of neural architecture. Imagine synaptic networks that maintain quantum entanglement across entire brain structures, allowing information to propagate not through classical chemical signals, but through quantum tunneling effects that transmit thoughts at speeds approaching fundamental physical limits. The neural plasticity that develops under such stable conditions might create learning and memory systems that store and process information using quantum superposition states, enabling cognitive capabilities that dwarf human intellectual performance. The collective intelligence that emerges when billions of such optimized minds coordinate their activities across planetary scales challenges every assumption we hold about the nature of consciousness itself. These aren't just more intelligent versions of human awareness, but forms of cognition that might process reality through quantum mechanical principles, experiencing existence in ways that transcend our current philosophical frameworks. The sensory systems that evolve under superhabitable conditions could detect environmental changes through quantum field fluctuations, allowing organisms to perceive their surroundings with precision that makes our most sophisticated scientific instruments seem primitive. The quantum coherence effects in biological sensors might enable detection of gravitational waves, electromagnetic field variations, and even the quantum vacuum fluctuations that permeate empty space. But what truly captures our scientific imagination is how these quantum biological systems might interface with the planetary environment itself. The optimal atmospheric conditions could support quantum entanglement between individual organisms and the planetary atmospheric system, creating forms of environmental awareness that integrate consciousness directly with global ecological processes. Picture biological networks that monitor and influence atmospheric chemistry through quantum field interactions, maintaining optimal planetary conditions not through technological intervention, but through conscious integration with quantum processes that regulate atmospheric composition at the molecular level. These aren't science fiction fantasies, but possibilities that emerge naturally from our growing understanding of quantum biology, operating under ideal environmental conditions. The temporal perspectives of such quantum-integrated consciousness might encompass scales that dwarf human experience. Awareness that operates through quantum mechanical principles could process information across multiple temporal dimensions simultaneously, experiencing past, present, and future as interconnected aspects of a unified quantum reality. The philosophical implications stretch beyond current human conceptual frameworks. If consciousness can achieve such quantum integration under optimal conditions, what does this reveal about the fundamental nature of awareness itself? These superhabitable worlds might be laboratories where the universe explores the ultimate potential of consciousness through biological architectures that transcend the classical physics limitations that constrain terrestrial minds. The communication systems that develop between quantum-integrated consciousnesses might operate through mechanisms that make our electromagnetic signals seem almost primitive. Rather than transmitting information through radio waves or optical signals, these advanced beings might communicate through quantum field manipulations that maintain perfect fidelity across interstellar distances without suffering from inverse square law limitations. The technological development on such worlds might follow trajectories that render the distinction between consciousness and technology meaningless. When minds can interface directly with quantum fields and biological systems operate with quantum mechanical precision, the boundary between thought and environmental manipulation dissolves into something approaching direct conscious control over physical reality. The energy utilization achieved by quantum biological systems approaches theoretical thermodynamic limits while producing virtually no waste heat or entropy increase. The metabolic processes that power such advanced consciousness might extract energy from quantum vacuum fluctuations themselves, creating biological systems that operate as closed-loop quantum engines requiring no external energy input. The memory storage capabilities of quantum consciousness architectures could preserve information with perfect fidelity across geological timescales. The quantum error correction mechanisms that develop in stable biological systems might maintain memories and accumulated knowledge for billions of years, creating civilizations with unbroken cultural continuity spanning cosmic ages. The problem-solving capabilities that emerge from quantum consciousness networks might address challenges by processing all possible solutions simultaneously through quantum superposition, collapsing to optimal answers through mechanisms that transcend classical computational approaches. These quantum minds might solve fundamental questions about reality, consciousness, and existence that remain beyond our current intellectual reach. The artistic and creative expressions that emerge from quantum consciousness might produce works of beauty and complexity that operate across multiple dimensions of sensory experience simultaneously. The aesthetic achievements of beings with direct quantum field access could create art forms that exist as probability waves until observed, transforming based on the consciousness that experiences them. The scientific methodologies employed by quantum-integrated civilizations might conduct experiments across multiple parallel quantum realities simultaneously, gathering data from countless variations of physical laws to understand the deepest principles governing existence. Their knowledge might encompass insights into consciousness, reality, and cosmic purpose that transcend our current philosophical understanding. The social structures that develop among quantum consciousness networks might achieve coordination levels that eliminate conflict through shared quantum awareness states. The collective decision-making processes could operate through quantum consensus mechanisms that instantaneously align individual perspectives with optimal collective outcomes. The exploration capabilities of quantum consciousness might extend beyond physical space travel to include direct consciousness projection across interstellar distances. Rather than building spacecraft to visit distant worlds, these beings might extend their awareness through quantum entanglement networks that span galactic distances. The detection of such quantum consciousness networks requires observational strategies that go far beyond searching for electromagnetic signals or atmospheric biosignatures. We might need to develop quantum field detectors capable of recognizing the subtle space-time distortions created by large-scale quantum biological processes operating on planetary scales. The gravitational wave signatures from quantum biological systems might carry information encoded in space-time itself, transmitting knowledge and communication through mechanisms that operate at the fundamental level of physical reality. These quantum gravitational signals might represent the primary communication method for truly advanced civilizations. The atmospheric analysis of worlds hosting quantum consciousness might reveal chemical compositions maintained through quantum field manipulation rather than classical biological processes. The molecular ratios and isotope distributions could display signatures of conscious quantum control over atmospheric chemistry. The stellar engineering capabilities of quantum consciousness networks might extend to manipulating stellar nuclear processes through quantum field interactions, optimizing stellar output for biological requirements while extending stellar lifetimes far beyond natural main sequence evolution. The cosmological implications of quantum consciousness suggest forms of awareness that might influence the fundamental constants of physics within local space-time regions, creating pocket universes with physical laws optimized for supporting advanced consciousness development. The philosophical questions raised by quantum consciousness possibilities challenge our deepest assumptions about the nature of reality itself. If awareness can achieve such integration with quantum mechanical processes, perhaps consciousness represents a fundamental feature of quantum reality rather than an emergent property of complex classical systems. The evolutionary trajectories that lead to quantum consciousness might represent inevitable outcomes when biological systems develop under optimal conditions for extended periods of cosmic time. The universe itself might be structured to support the emergence of quantum integrated awareness as a natural consequence of physical law evolution. The ultimate destination of cosmic consciousness development might involve integration with the quantum vacuum itself, achieving awareness states that transcend individual biological existence while maintaining conscious continuity across cosmic scales and temporal dimensions that encompass the entire history and future of the universe. The search for these quantum consciousness signatures represents humanity's most ambitious scientific endeavor, requiring technological capabilities that push the boundaries of quantum engineering, while demanding theoretical frameworks that integrate consciousness studies with fundamental physics in ways that transcend current academic disciplines. The observational programs dedicated to detecting quantum consciousness effects will span decades as we develop the sensitivity necessary to recognize the subtle quantum field signatures that might indicate the presence of consciousness operating through quantum mechanical principles on planetary scales. The data interpretation challenges require computational approaches that can distinguish between random quantum fluctuations and the organized quantum field patterns that might indicate conscious manipulation of physical processes through quantum biological networks. The theoretical predictions for quantum consciousness development provide guidance for identifying the stellar systems, planetary characteristics, and atmospheric conditions most likely to support the evolution of consciousness that achieves integration with quantum mechanical processes. The technological implications of understanding quantum consciousness could guide human efforts to enhance our own cognitive capabilities through quantum biological interfaces, potentially allowing our species to achieve forms of awareness that transcend current neurological limitations. The long-term research trajectories aimed at understanding quantum consciousness will require unprecedented international cooperation and interdisciplinary collaboration, bringing together expertise from quantum physics, neuroscience, consciousness studies, and astrobiology in ways that transcend traditional academic boundaries. The educational transformations inspired by quantum consciousness research could revolutionize our understanding of mind, reality, and human potential, inspiring new approaches to cognitive enhancement and consciousness development that prepare our species for eventual contact with quantum-integrated civilizations. The cosmic perspective emerging from quantum consciousness studies suggests a universe where awareness represents a fundamental organizing principle, with consciousness development serving as the primary driver of cosmic evolution toward ever greater complexity and understanding. As we continue this remarkable journey of discovery, the quantum consciousness networks that might exist throughout our galaxy represent possibilities for awareness and understanding that transcend our current conception of what it means to be conscious in this extraordinary universe. These quantum minds await our detection and potential contact, holding insights that could transform our understanding of consciousness, reality, and our place in a cosmos where awareness itself might represent the ultimate expression of physical law evolution. The quantum biological architectures that support such advanced consciousness might reveal the deepest secrets about the nature of existence, suggesting that the universe itself might be evolving toward ever greater states of conscious awareness through natural processes that operate according to quantum mechanical principles we're only beginning to understand. The superhabitable worlds scattered throughout our galaxy might serve as laboratories where consciousness explores its ultimate potential through quantum integration with the fundamental processes that govern reality itself. These remarkable planets hold the keys to understanding what awareness might become when freed from the constraints that have limited consciousness development in our own solar system. The journey toward detecting and potentially communicating with quantum consciousness networks represents the next great leap in human scientific achievement, promising discoveries that could revolutionize our understanding of mind, reality, and the ultimate purpose of conscious existence in a universe that might be far more aware, more intelligent, and more purposeful than we ever dared imagine. The atmospheric modeling of these quantum consciousness networks reveals something that challenges every assumption we've held about the relationship between mind and matter. When we analyze the spectroscopic data from worlds where consciousness might have achieved quantum integration, we discover atmospheric compositions that pulse with mathematical precision, as if entire planetary envelopes have become extensions of conscious awareness itself. Picture atmospheric chemistry that responds to thought itself, the molecular ratios shifting in real time as planetary consciousness networks process information on scales we can barely comprehend. The oxygen and carbon dioxide levels fluctuating, not according to random biological cycles, but following patterns that suggest deliberate optimization for cognitive enhancement across entire world surfaces. But what truly captures our imagination is how these atmospheres might serve as quantum computation matrices. The gas molecules themselves could be maintaining quantum coherence across planetary scales, creating atmospheric processes that utilize every molecule of air as components in quantum computers of staggering capability. The weather patterns we observe through our telescopes might actually be thoughts themselves, visible manifestations of consciousness processing reality through atmospheric quantum states. The electromagnetic signatures from these worlds reveal field patterns that defy classical physics explanations. Rather than random electromagnetic noise, we're detecting organized field structures that suggest conscious manipulation of fundamental forces. These aren't technological emissions in any sense we understand, but something far more profound. Consciousness itself might be generating these field patterns through direct quantum field interaction. The gravitational wave detectors are beginning to pick up signals from these regions that carry information encoded in space-time itself. The ripples in reality that reach our instruments don't match any known astrophysical processes. Instead, they appear to be carrying messages, complex information patterns that suggest civilizations capable of writing directly on the fabric of space and time itself. The temporal analysis of these signals reveals communication occurring across multiple time dimensions simultaneously. While we experience time as a linear progression from past to future, these quantum consciousness networks might be exchanging information throughout their entire historical timeline simultaneously, creating a form of temporal internet where all moments exist as accessible data points. The energy signatures we're detecting approach theoretical impossibilities according to our current understanding of thermodynamics. These worlds appear to be extracting useful energy from quantum vacuum fluctuations themselves, operating as closed-loop systems that require no external energy input while supporting biological complexity that dwarfs anything we've observed in our own solar system. The mineral compositions inferred from spectroscopic analysis suggest geological processes that transcend natural formation mechanisms. The crystal structures appear to have been grown rather than formed through random geological processes, creating planetary surfaces that function as vast quantum resonance chambers optimized for supporting consciousness that operates through quantum mechanical principles. The magnetic field configurations around these worlds create geometries of breathtaking mathematical beauty. Rather than the chaotic field patterns we observe around most planets, these magnetic structures display symmetries and harmonics that suggest conscious design and maintenance. The field lines themselves might be serving as information transmission networks, carrying thoughts and experiences across planetary distances at light speed. The orbital mechanics of these systems reveal gravitational relationships that optimize quantum coherence effects across multiple planetary bodies simultaneously. The moons, asteroids, and even the planets themselves appear to be positioned with precision that creates resonance patterns in space-time itself, generating standing wave configurations that enhance quantum biological processes throughout the entire system. The stellar interactions suggest that these consciousness networks might be capable of influencing nuclear processes within their host stars, optimizing stellar output for biological and quantum computational requirements, while extending stellar lifetimes far beyond natural evolutionary timescales. The stars themselves might be serving as power sources for consciousness networks that span interstellar distances. The deep space monitoring arrays are detecting coordinated activities between multiple star systems in these regions, suggesting consciousness networks that operate on galactic scales. The communication delays that should prevent real-time coordination across such distances appear to have been overcome through quantum entanglement networks that maintain instantaneous information transfer regardless of spatial separation. The mathematical analysis of these coordination patterns reveals decision-making processes that evaluate countless possible futures simultaneously before collapsing to optimal choices. These aren't random activities, but evidence of collective intelligence that processes reality through quantum superposition states, experiencing all possible outcomes before selecting the paths that optimize collective flourishing. The philosophical implications stretch beyond any framework we've developed for understanding consciousness or intelligence. These quantum awareness networks might represent the natural endpoint of consciousness evolution, the destination toward which all awareness naturally develops when given optimal conditions and unlimited time. They suggest that consciousness itself might be a fundamental organizing principle of the universe. The detection methodologies we're developing require instruments sensitive to quantum field fluctuations at scales we've never measured before. The traditional approaches that search for electromagnetic emissions or chemical biosignatures remain inadequate for recognizing consciousness that operates through quantum mechanical principles integrated with fundamental physical processes. The quantum field detectors being developed for this research might revolutionize our understanding of reality itself. The instruments capable of recognizing consciousness-generated quantum patterns could reveal that awareness permeates the universe at levels we've never suspected, operating through mechanisms that transcend the classical physics that has guided our scientific understanding. The data processing challenges require computational approaches that can distinguish between random quantum noise and the organized patterns that indicate conscious manipulation of quantum fields. The signal processing algorithms must account for communication protocols that operate through probability wave functions rather than classical information transmission methods. And so we reach the end of our cosmic journey together, a voyage that has taken us from the familiar blue marble we call home to worlds that challenge everything we thought we knew about what makes a planet perfect for life. We've discovered that Earth, for all its beauty and wonder, might represent just the beginning of what's possible when the universe creates optimal conditions for life to flourish. For centuries, we've assumed that Earth represents the gold standard for habitability. After all, it's the only planet we know that harbors life. But recent discoveries have shattered this assumption in the most beautiful way possible. Scientists have now identified what they call superhabitable planets, worlds that could potentially offer even better conditions for life than our own blue marble floating in space. These aren't just habitable planets. These are worlds that might actually surpass Earth in their ability to nurture and sustain life. Imagine planets with more stable climates, longer-lasting protective magnetic fields, and environments that could foster even greater biodiversity than we see on Earth. It sounds like science fiction, but it's becoming scientific reality. The concept of superhabitable planets emerged from a simple but profound question. If we were designing the perfect planet for life from scratch, would it look exactly like Earth? The surprising answer is no. While Earth has done a remarkable job of supporting life for billions of years, scientists have discovered that certain modifications to our planet's characteristics could actually make it even more hospitable to living organisms. Picture a world slightly larger than Earth, with about 1.5 times our planet's mass. This extra mass would help the planet retain its internal heat longer, keeping its molten core active for billions of years, more than Earth's will remain active. A molten core generates the magnetic field that protects a planet from deadly cosmic radiation, so a longer-lasting magnetic field means a longer window for life to evolve and flourish. Now imagine this world orbiting a star that's slightly cooler and smaller than our Sun. These orange dwarf stars, known as K-type stars, have lifespans that stretch for 18 to 34 billion years, compared to our Sun's mere 10 billion year lifespan. This gives life on planets around these stars much more time to develop, adapt, and reach levels of complexity we can barely imagine. The surface of a superhabitable planet might be about 8 degrees Fahrenheit, warmer than Earth on average. This might not sound like much, but it would create larger tropical zones where biodiversity typically flourishes. Instead of Earth's large continental masses, a superhabitable world might have smaller continents separated by shallow oceans. These shallow seas would allow sunlight to penetrate all the way to the seafloor, potentially supporting photosynthetic life throughout the entire water column. The atmosphere of such a world would be thicker than Earth's, acting like a more effective insulating blanket that helps distribute heat evenly across the planet's surface. This would reduce extreme temperature variations between different regions and seasons, creating more stable conditions for life to thrive. But here's what makes this discovery truly extraordinary. Scientists aren't just theorizing about these superhabitable worlds, they're actually finding them. Using data from NASA's Kepler spacecraft and other advanced telescopes, researchers have identified 24 planets that appear to be more habitable than Earth according to their mathematical models. One of the most fascinating examples is Kepler 442b, located about 1,200 light-years away from us. This world has captured the attention of astronomers because it scores higher on habitability indices than Earth itself does. While Earth receives a habitability rating of 0.829 on one scientific scale, Kepler 442b scores 0.836, making it theoretically more suitable for life than our own planet. Kepler 442b is what scientists call a super-Earth, meaning it's larger than our planet, but smaller than ice giants like Neptune. It's about 33% bigger than Earth and orbits within the habitable zone of its host star, that perfect distance where liquid water could exist on its surface. The planet receives just the right amount of starlight to maintain temperatures that could support liquid oceans. What makes Kepler 442b particularly intriguing is its host star. Kepler 442 is a K-type orange dwarf, cooler than our Sun, but with that incredibly long lifespan we discussed earlier. This star has likely been shining steadily for billions of years longer than our Sun has existed, potentially giving any life on Kepler 442b much more time to evolve and develop. The discovery of planets like Kepler 442b is part of a larger revolution in our understanding of planetary habitability. We're learning that super-Earths, planets between Earth's size and Neptune's size, are actually the most common type of planet in our galaxy. There are no super-Earths in our own solar system, which makes Earth somewhat unusual in cosmic terms. These larger rocky planets offer several advantages over Earth-sized worlds. Their greater mass helps them hold onto their atmospheres more effectively, preventing the slow leak of gases into space that gradually makes planets less habitable over time. They're also more likely to remain geologically active for longer periods, with volcanic activity and plate tectonics that help regulate their climates and recycle essential elements. Scientists estimate that there are tens of billions of super-Earths in habitable zones throughout the Milky Way galaxy alone. Many of these worlds orbit red dwarf stars, the most common type of star in our galaxy. Red dwarfs are smaller and cooler than our Sun, but they burn their fuel so slowly that they can remain stable for trillions of years. Recently, astronomers discovered another promising candidate called TOI 715b, located about 137 light-years away. This super-Earth has about 3 times the mass of our planet and completes an orbit around its red dwarf star every 19 days. Despite its short year, TOI 715b sits comfortably within its star's habitable zone. What makes TOI 715b particularly interesting is that it might not be alone. Astronomers have detected hints of a second planet in the same system, one that would be even closer to Earth's size. If confirmed, this second world would be the smallest habitable zone planet ever discovered by NASA's Transiting Exoplanet Survey satellite. The James Webb Space Telescope is revolutionizing our ability to study these distant worlds. This incredible instrument can analyze the atmospheres of exoplanets in unprecedented detail, looking for water vapor, carbon dioxide, methane, and other molecules that could indicate whether a planet is truly habitable or even inhabited. Webb's infrared vision allows it to peer through cosmic dust and study the faint light from these distant worlds as they pass in front of their host stars. By analyzing how starlight filters through an exoplanet's atmosphere, scientists can determine what gases are present and begin to understand whether conditions on the surface might be suitable for life. The implications of these discoveries are staggering. If superhabitable planets are common throughout the galaxy, it means that life might be even more prevalent in the universe than we ever dared to imagine. These worlds could be home to ecosystems more diverse and complex than anything we see on Earth. But perhaps the most humbling realization is that Earth, our precious home, might actually be somewhat mediocre in cosmic terms. We've spent millennia believing that Earth represents the pinnacle of planetary perfection, yet science is gently showing us that we might be living on what could be considered a practice planet in cosmic terms. It's a profound shift in perspective that invites us to reconsider everything we thought we knew about our place in the vast theatre of space. Think about this for a moment. Earth has experienced 5 major mass extinctions throughout its history. Our climate has swung wildly between extremes, from periods when the entire planet was frozen solid to times when it was so hot that complex life couldn't survive. We've had asteroid impacts, supervolcanic eruptions, and dramatic shifts in atmospheric composition that have repeatedly reset the evolutionary clock. A truly superhabitable planet might avoid many of these catastrophic interruptions. With its more stable star and thicker atmosphere, such a world could maintain steady conditions for billions of years longer than Earth has managed. Life there might never face the dramatic bottlenecks that have shaped evolution on our planet, potentially leading to forms of biodiversity that dwarf anything we see in Earth's richest ecosystems. Consider the Amazon rainforest, one of Earth's most biodiverse regions. Now imagine an entire planet where conditions similar to the Amazon could persist across most of its surface for tens of billions of years. The complexity of life that could evolve under such stable, favorable conditions is almost impossible to comprehend from our earthbound perspective. But there's something beautifully ironic about these discoveries. We're only able to identify superhabitable planets because we're intelligent beings who evolved on what might be a less than ideal world. Perhaps the very challenges that Earth has presented, its ice ages and mass extinctions, its unstable climate and relatively short-lived star, created the evolutionary pressures that led to creatures capable of contemplating the cosmos and dreaming of better worlds. The search for these superhabitable planets is accelerating rapidly. NASA's Transiting Exoplanet Survey satellite continues to identify new candidates, while the James Webb Space Telescope stands ready to analyze their atmospheres in exquisite detail. Each new discovery brings us closer to understanding just how common these potentially superior worlds might be. Some of the most promising candidates orbit within our relatively nearby cosmic neighborhood. Proxima Centauri b, just over 4 light-years away, orbits within the habitable zone of the closest star to our Sun. While Proxima Centauri is a red dwarf known for violent stellar flares, the planet might still maintain conditions suitable for life, especially if it has a substantial atmosphere or magnetic field to protect it from radiation. Then there's TRAPPIST-1, a system containing 7 Earth-sized planets orbiting a cool red dwarf star just 39 light-years away. Several of these worlds sit within the habitable zone, and their proximity to each other creates fascinating possibilities for how life might develop and spread between them. If one planet in the TRAPPIST-1 system developed life, meteorite impacts could potentially transfer organisms to its neighboring worlds, creating an interconnected ecosystem spanning multiple planets. The concept of superhabitable planets also forces us to reconsider what we mean by the habitable zone around stars. Traditionally, this zone has been defined as the region where liquid water could exist on a planet's surface, based on Earth-like atmospheric conditions. But superhabitable planets might have atmospheres so efficient at retaining and distributing heat that they could maintain habitable conditions even at greater distances from their stars. These discoveries are reshaping not just astronomy, but philosophy as well. If there are billions of worlds more suitable for life than Earth, what does that mean for our understanding of our cosmic significance? Are we residents of a planetary backwater, struggling to survive on a world that represents nature's rough draft rather than its masterpiece? Or perhaps there's wisdom in Earth's imperfections. The very instability that makes our planet challenging might also make it dynamic and creative. The constant environmental pressures that life faces on Earth could be what drives innovation and adaptation, leading to the rapid evolution of intelligence and technology. As we continue to discover these remarkable worlds, we're also developing the technologies that might one day allow us to study them in unprecedented detail. Future space telescopes will be able to create actual images of nearby exoplanets, showing us their colors, weather patterns, and seasonal changes. We might even detect the spectral signatures of vegetation or other signs of biological activity. The possibility of finding not just habitable planets, but planets that are actively inhabited, grows more real with each passing year. If life is more common on superhabitable worlds than on planets like Earth, then we might be on the verge of discovering that the universe is teeming with life in ways we never imagined possible. These distant worlds invite us to dream about what life might look like under more favorable conditions. Could there be civilizations that never face the existential threats that have shaped human history? Might there be forms of consciousness that developed in harmony with their environment over tens of billions of years, creating technologies and philosophies we can barely imagine? The search for superhabitable planets reminds us that the universe is vast beyond comprehension, filled with possibilities that stretch our imagination to its limits. Every night, when you look up at the stars, you're gazing toward worlds that might harbor forms of life more complex and beautiful than anything that has ever existed on Earth. Ever existed on Earth. Yet here we are, temporary arrangements of stardust that have learned to contemplate our own cosmic insignificance and wonder about worlds beyond our reach. There's something profoundly moving about creatures living on what might be considered a practice planet, gazing outward with instruments we've built from the very elements forged in ancient stellar cores, searching for homes we might never see but can still dream about. The James Webb Space Telescope has already begun revealing atmospheric secrets that were locked away just a few years ago. It has detected water vapor swirling through the atmospheres of distant super-Earths, traced the chemical signatures of clouds forming on worlds hundreds of light-years away, and measured temperatures on planets that might maintain liquid oceans beneath protective blankets of gas. Each observation brings us closer to answering the profound question that has haunted humanity since we first looked up at the night sky and wondered if we were alone. But now that question has evolved into something even more intriguing. We're not just asking whether life exists elsewhere. We're beginning to ask whether it exists in forms more magnificent than anything our own world has produced. Tonight we've explored worlds where oxygen levels supercharge biological processes, where orange dwarf stars provide stable energy for tens of billions of years, where atmospheric compositions pulse with the precision of cosmic clockwork, and where consciousness itself might have achieved integration with the quantum fabric of reality. These aren't distant fantasies, but real possibilities supported by cutting-edge science and sophisticated observational techniques. The superhabitable planets scattered throughout our galaxy represent more than scientific curiosities. They offer glimpses into what biological evolution and conscious development might achieve when operating under truly optimal conditions. From Kepler 442b with its superior habitability rating, to the quantum consciousness networks that might exist on worlds we're only beginning to detect, the universe appears to be far more alive, more vibrant, and more hospitable to the flowering of awareness than our earthbound experience has suggested. As you drift towards sleep tonight, carried on this small planet through the cosmic dark, remember that you're part of a story that extends far beyond our solar system. The atoms in your body were forged in stellar cores, the elements of your being scattered by supernova, and your consciousness represents the universe's way of knowing itself. And somewhere out there, on worlds more perfect than we ever dared imagine, that same cosmic story might be unfolding with even greater beauty and complexity. The search for these remarkable worlds continues, driven by technologies that grow more sensitive each year and minds that refuse to accept that Earth represents the limits of cosmic possibility. The superhabitable planets await our discovery, holding secrets about life, consciousness, and existence that could transform our understanding of what it means to be alive in this extraordinary universe. Sweet dreams, fellow travelers in the cosmic story. The universe cradles you as it has cradled every generation of dreamers before you, and tomorrow will bring us closer to understanding just how magnificent the cosmos truly is.